Imagine if every night when you looked up at the sky, you could see invisible magnetic tornadoes powerful enough to tear atoms apart, or witness entire galaxies dancing together in slow-motion collisions that span millions of years. What if the most incredible bedtime stories were not fairy tales, but the actual wonders happening right now in the universe above your head? Tonight, we journey through 60 cosmic mysteries so extraordinary they surpass any fiction, gently carrying your mind toward peaceful rest among the infinite stars. 1. Magnetars. Deep in the constellation Aquila, roughly 15,000 light-years from Earth, lies an object so magnetically powerful that it could erase every credit card on our planet from half the distance to the moon. This is a magnetar, and it represents one of the most extreme environments that physics allows to exist in our universe. To understand just how extraordinary magnetars are, we must first grasp the incredible journey that creates them. When a star, at least 10 times more massive than our Sun, reaches the end of its life, it undergoes a catastrophic collapse that happens in less than a second. The core, once the size of Earth, compresses down to a sphere only 12 miles across, yet retains more mass than our entire Sun. This creates a neutron star, where matter becomes so dense that a teaspoon would weigh as much as Mount Everest. But magnetars are neutron stars with an additional twist of cosmic extremes. During their violent birth, the magnetic field lines become twisted and amplified to strengths that defy human comprehension. A magnetar possesses a magnetic field 1 quadrillion times stronger than Earth's protective magnetic shield. This field is so powerful that it actually warps the shape of atoms themselves, stretching them into elongated cylinders. The surface of a magnetar experiences starquakes that release more energy in 1/10 of a second than our Sun produces in 100,000 years. These cosmic tremors cause the star's crust to crack and shift, sending out beams of X-rays that can be detected by our satellites across vast distances. As you drift towards sleep tonight, imagine these stellar lighthouses spinning in the cosmic darkness, their magnetic fields creating invisible sculptures in the fabric of space-time itself, reminding us that even in the universe's most violent places, there exists a strange and terrible beauty. 2. The multiverse theory. As you settle into the comfort of your bed tonight, consider this possibility. There may be countless other versions of you doing the exact same thing, but in universes where the laws of physics unfold just slightly differently. This is the profound suggestion of the multiverse theory, one of the most mind-expanding concepts in modern cosmology. The multiverse theory emerges from our understanding of cosmic inflation, the period immediately after the Big Bang when space itself expanded faster than the speed of light. Imagine a balloon being inflated, but instead of one smooth surface, different regions expand at different rates, creating separate bubble universes within an infinite cosmic foam. Each bubble represents a complete universe with its own space, time, and physical laws. In some of these parallel universes, the fundamental constants that govern reality are tweaked just enough to create entirely different cosmic stories. There might be universes where gravity is slightly weaker, allowing stars to burn for trillions of years instead of billions. Other universes might have stronger electromagnetic forces, preventing atoms from forming and leaving only a sea of fundamental particles drifting through space. The most intriguing possibility is that there are universes nearly identical to our own, where history unfolded almost exactly the same way, but with tiny variations. Perhaps there is a universe where you chose a different career, or where the dinosaurs never went extinct, or where humans developed the ability to see ultraviolet light. These infinite variations play out across the cosmic stage like an endless symphony of possibility. The multiverse theory suggests that everything that can happen, does happen, somewhere in the vast expanse of parallel realities. As you close your eyes and let your consciousness drift, you join an infinite number of other versions of yourself, all settling into sleep across the boundless landscape of existence, each dreaming their own unique dreams in their own corner of infinity. 3. Brown dwarfs. Floating in the cold depths of space are cosmic wanderers that represent one of the universe's most poignant stories of almost but not quite. These are brown dwarfs, objects that formed like stars but never quite achieved the nuclear fusion necessary to truly shine. They exist in a lonely middle ground between planets and stars, too massive to be one, too small to be the other. Brown dwarfs begin their existence in the same stellar nurseries where true stars are born. They condense from clouds of gas and dust, growing larger as gravity pulls more material toward their center. But unlike their more successful siblings, brown dwarfs never accumulate enough mass to ignite the fusion reactions that would transform them into brilliant stars. They need to be at least 8% the mass of our Sun to achieve this cosmic ignition, and they fall just short of this crucial threshold. Without nuclear fusion to generate energy and light, brown dwarfs can only slowly radiate away the heat from their original formation. They begin their lives glowing with a dim red light, warm from the gravitational energy released during their collapse. But as millions of years pass, they gradually cool and fade, eventually becoming invisible to optical telescopes. Their surface temperatures drop from over 2000 degrees to eventually match the coolness of a pleasant spring day on Earth. These failed stars drift through the galaxy like cosmic ghosts, detectable only by the faint infrared radiation they emit as they cool. Some brown dwarfs wander alone through interstellar space, while others orbit more successful stars as dim companions. Recent discoveries have revealed that some brown dwarfs even have their own weather systems, with clouds of iron droplets and silicate dust creating storms across their surfaces. As you prepare for sleep, think of these gentle cosmic wanderers, glowing softly in the darkness like dying embers from the universe's stellar forge, reminding us that not all celestial objects are destined for the dramatic lives of stars, but can find their own quiet dignity in the peaceful spaces between. 4. Zero-point energy. Even in the most perfect vacuum that science can create, where every atom has been removed and space appears completely empty, the universe still hums with an invisible energy that never stops fluctuating. This is zero-point energy, the quantum mechanical phenomenon that ensures true emptiness can never really exist, and it represents one of the most mysterious aspects of reality itself. To understand zero-point energy, we must venture into the strange world of quantum mechanics, where the familiar rules of everyday life no longer apply. According to quantum theory, energy cannot remain perfectly still or reach absolute zero, even at the coldest possible temperature. Instead, even empty space must contain a minimum amount of energy that causes it to constantly vibrate and fluctuate at the smallest scales imaginable. These quantum fluctuations are not merely theoretical curiosities. They manifest as virtual particles that spontaneously appear and disappear in pairs throughout empty space, existing for such brief moments that they seem to borrow energy from the future and pay it back before the universe notices. Electrons and positrons pop into existence, dance together for an infinitesimal fraction of a second, and then annihilate each other, leaving only the faintest trace of their quantum waltz. The implications of zero-point energy extend far beyond empty space. It influences the behavior of atoms, affects the emission of light from stars, and may even play a role in the mysterious dark energy that is accelerating the expansion of our universe. Some scientists speculate that if we could somehow harness zero-point energy, we might access an unlimited source of power hidden within the fabric of space itself. As you lie in the quiet darkness of your room, remember that the space around you is not truly empty, but filled with this constant quantum activity. Every cubic centimeter contains enough zero-point energy to power civilization for billions of years. If only we knew how to tap into this invisible reservoir that makes even nothingness vibrate with potential. 5. Galaxy collisions. In the cosmic dance that has been unfolding for billions of years above our heads, entire galaxies are slowly waltzing toward each other in gravitational embraces that will reshape the very structure of space. These galaxy collisions represent some of the most majestic and patient events in the universe, unfolding over hundreds of millions of years with a grace that makes human timescales seem like fleeting moments. Our own Milky Way galaxy is currently engaged in such a cosmic choreography with our nearest major neighbor, the Andromeda Galaxy. At this very moment, Andromeda is approaching us at roughly 250,000 miles per hour. Yet it will still take approximately 4.5 billion years before the two galaxies begin to merge. This collision will transform both galaxies, eventually creating a single, larger elliptical galaxy that astronomers have already nicknamed Milky Way. Despite the dramatic name collision, galaxy mergers are surprisingly gentle affairs. The distances between individual stars are so vast that when galaxies merge, very few stars actually collide with each other. Instead, the gravitational interactions reshape the orbits of billions of stars, flinging some into new trajectories and drawing others closer to the combined galactic center. The spiral arms that give galaxies their distinctive shapes become disrupted and reformed into new patterns, During these cosmic mergers, the supermassive black holes at the centers of each galaxy eventually spiral toward each other, creating some of the most energetic events the universe can produce. As they dance closer together, they generate gravitational waves that ripple through space-time itself, carrying away energy until the two black holes finally merge into one even more massive object. Tonight, as you settle into sleep, remember that our galaxy is slowly dancing through space toward this inevitable cosmic union. In the deep future, beings looking up at the night sky will see a completely different arrangement of stars, shaped by a collision so gradual and gentle that life could continue uninterrupted throughout the entire process of galactic transformation. Cosmic Wonders, 6 to 15, complete script, 300 words each. 6. Event Horizons. Imagine standing at the edge of a cosmic point of no return, where the very concept of escape becomes meaningless and the normal flow of time begins to stretch like warm honey. This is the event horizon, the invisible boundary that surrounds every black hole and represents one of the most profound and mysterious frontiers that physics has revealed to us. The event horizon is not a physical surface that you could touch or see, but rather a mathematical boundary in space-time itself. It marks the distance from a black hole where the escape velocity equals the speed of light. Since nothing in our universe can travel faster than light, anything that crosses this boundary becomes permanently trapped, destined to spiral inexorably toward the black hole's center, or singularity. What makes event horizons truly fascinating is how they warp our understanding of time and space. According to Einstein's theory of relativity, time itself slows down in strong gravitational fields. As you approached a black hole's event horizon, time would begin to dilate dramatically. To an outside observer watching you fall toward the black hole, your movements would appear to slow down. Your image would redshift and fade, but you would never actually seem to cross the horizon. From your perspective, however, you would pass through normally, though you would notice the universe behind you appearing to speed up and age rapidly. The size of an event horizon depends entirely on the mass of the black hole it surrounds. A black hole with the mass of our Sun would have an event horizon only about 3 miles in radius, while the supermassive black hole at the center of our galaxy has an event horizon larger than the orbit of Mercury. Some theoretical black holes could have event horizons spanning billions of miles, creating regions of spacetime so warped that entire solar systems could fit within their boundaries. As you drift toward sleep tonight, contemplate these invisible spheres scattered throughout the cosmos, where the familiar laws of cause and effect become twisted into forms that challenge our deepest understanding of reality itself. 7. Cosmic background radiation, surrounding us at every moment, penetrating every cubic inch of space in the universe, is the faint whisper of creation itself, gentle electromagnetic glow that represents the oldest light we can possibly observe. This is the cosmic microwave background radiation, the afterglow of the Big Bang, and it carries within its subtle fluctuations the blueprint for every galaxy, star, and planet that would eventually form. To understand this cosmic relic, we must journey back to when the universe was only 380,000 years old, a mere infant compared to its current age of nearly 14 billion years. During this epoch, called recombination, the universe had finally cooled enough for the first stable atoms to form. Before this moment, space was filled with a hot, dense plasma of protons, electrons, and photons, all interacting constantly with each other. Light could not travel freely, because it would immediately scatter off the charged particles, making the universe completely opaque. But when the temperature dropped sufficiently, electrons began combining with protons to form the first hydrogen atoms. Suddenly, photons were no longer scattered by free electrons and could travel unimpeded across the cosmos. This first light, originally blazing with the intensity of the surface of the Sun, has been traveling through space for over 13 billion years, cooling and redshifting as the universe expanded around it. Today, this ancient light reaches us as microwave radiation with a temperature just 2.7 degrees above absolute zero. It is remarkably uniform in all directions, but contains tiny fluctuations of just a few parts in 100,000 that represent the seeds of all cosmic structure. These minute temperature differences correspond to regions of slightly different density in the early universe, and it was these small variations that eventually grew, under the influence of gravity, into the cosmic web of galaxies we observe today. Every time you tune a television to static, About 1% of that interference comes from this primordial light, connecting you directly to the moment when the universe first became transparent and the cosmic dawn began. 8. Stellar nurseries. In the cold depths between the stars, vast clouds of gas and dust drift through space like cosmic gardens where new suns are slowly taking root. These stellar nurseries, also known as nebulae, represent some of the most beautiful and creative regions in our galaxy, where the raw materials of hydrogen and helium, left over from the Big Bang, are transformed into the blazing furnaces that light up the cosmos. These stellar birthplaces can span hundreds of light-years across and contain enough material to create thousands of stars. The Eagle Nebula, one of the most famous star-forming regions, stretches across roughly 70 light-years and contains towering pillars of gas and dust that dwarf our entire solar system. Within these pillars, gravity slowly pulls material together, concentrating it into ever-denser clumps that will eventually ignite as new stars. The process of star formation unfolds over millions of years with patience that exceeds human comprehension. It begins when shock waves from nearby supernova or collisions between gas clouds cause regions within a nebula to start collapsing under their own gravity. As these regions contract, they heat up, eventually reaching temperatures of millions of degrees. When the core becomes hot enough, nuclear fusion begins, transforming hydrogen into helium and releasing the tremendous energy that causes a star to shine. Not all protostars succeed in this cosmic endeavor. Some remain as brown dwarfs, while others are disrupted by radiation from nearby massive stars before they can complete their formation. The most successful stellar nurseries can continue producing new stars for tens of millions of years, creating entire stellar associations and open clusters that drift through the galaxy together. These nebulae glow with ethereal beauty, illuminated by the ultraviolet radiation from the young, hot stars they have created. The gas clouds fluoresce in brilliant colors: red from hydrogen, green from oxygen, and blue from other trace elements, creating some of the most stunning images captured by our space telescopes. As you settle into sleep tonight, imagine these cosmic gardens scattered throughout our galaxy, patiently nurturing the next generation of stars that will light up the universe for billions of years to come. 9. Strange matter. Deep within the crushing cores of neutron stars, where matter is compressed to densities beyond human comprehension, there may exist a form of matter so exotic that it represents an entirely different phase of reality itself. This is strange matter, composed of particles that exist nowhere else in the universe and possess properties that challenge our fundamental understanding of how matter behaves under the most extreme conditions imaginable. To understand strange matter, we must first venture into the realm of quantum chromodynamics, where protons and neutrons are no longer indivisible particles, but are revealed to be made of even smaller constituents called quarks. Under normal conditions, quarks are always confined within larger particles, bound together by the strong nuclear force. But in the incredibly dense cores of neutron stars, where the pressure exceeds anything found elsewhere in the universe, this confinement may break down entirely. Strange matter theoretically consists of roughly equal numbers of up quarks, down quarks, and strange quarks, all existing freely rather than being bound within individual protons and neutrons. This creates a substance that is perfectly stable and has a lower energy state than any normal matter. If strange matter exists, it would be the ultimate form of matter in our universe, more stable than the atoms that make up everything we see around us. The implications of strange matter are both fascinating and unsettling. Some theories suggest that if even a small amount of strange matter came into contact with normal matter, it could convert that normal matter into strange matter as well, creating a chain reaction that could theoretically transform entire planets or stars. Fortunately, strange matter, if it exists at all, appears to be confined to the cores of the most massive neutron stars, where the extreme conditions necessary for its formation can be sustained. Strange matter represents the ultimate frontier of our understanding of fundamental physics, existing at the intersection of quantum mechanics, nuclear physics, and general relativity. As you drift toward sleep, contemplate these exotic islands of alien matter hidden within distant stars, where the familiar rules of chemistry and physics give way to stranger and more wonderful possibilities than we have yet imagined. 10. The Great Attractor. Somewhere in the direction of the constellation Hydra, hidden behind the disk of our own Milky Way galaxy, lies one of the most mysterious gravitational anomalies in the observable universe. The Great Attractor is pulling our galaxy, along with thousands of others, toward itself at a speed of over 1.4 million miles per hour. Yet its exact nature remains one of cosmology's most intriguing puzzles. This cosmic mystery was first discovered when astronomers noticed that our local group of galaxies, including the Milky Way and Andromeda, is moving through space much faster than can be explained by the expansion of the universe alone. Something massive was pulling us, along with all the nearby galaxy clusters, in a specific direction. When they traced back the source of this gravitational influence, they found it centered on a region of space, roughly 150 to 250 million light-years away. The challenge in studying the Great Attractor is that it lies directly behind the plane of our galaxy, in what astronomers call the zone of avoidance. The thick concentration of stars, gas, and dust in the Milky Way's disk blocks our view of this region, making it nearly impossible to observe what lies beyond. It is like trying to study a distant mountain while looking through a dense forest. The intervening material obscures our vision and leaves us guessing about what creates such powerful gravitational attraction. Recent observations suggest that the Great Attractor is not a single massive object, but rather a complex structure of galaxy clusters, superclusters, and dark matter concentrations. Some astronomers believe it may be part of an even larger structure called the Shapley supercluster, a massive concentration of galaxies that contains some of the densest regions of matter in the observable universe. What makes this cosmic phenomenon even more remarkable is its sheer scale of influence. The Great Attractor affects the motion of galaxies across a region hundreds of millions of light-years across, demonstrating the incredible reach of gravity when operating on cosmic scales. As you prepare for sleep tonight, remember that you are quietly riding aboard a galaxy that is being drawn through space by this invisible hand, participating in a cosmic journey toward a destination we cannot yet clearly see. 11. Hawking radiation. In one of the most elegant and counterintuitive discoveries of modern physics, Stephen Hawking revealed that black holes, those cosmic voids from which nothing can escape, actually glow with a faint radiation and slowly evaporate over unimaginably long periods of time. This phenomenon, known as Hawking radiation, emerges from the strange quantum mechanical properties of empty space itself and suggests that even the most permanent-seeming objects in the universe are gradually dissolving back into the cosmic background. The mechanism behind Hawking radiation lies in the quantum fluctuations that constantly occur in empty space. Even in a perfect vacuum, virtual particle pairs spontaneously appear and disappear in tiny fractions of a second. Normally, these particle and hyperparticle pairs annihilate each other almost immediately, leaving no permanent trace of their brief existence. However, near the event horizon of a black hole, something remarkable happens to this process. When a virtual particle pair appears just outside the event horizon, the intense gravitational field can separate the two particles before they have a chance to annihilate each other. One particle falls into the black hole while its partner escapes to infinity, becoming real radiation that can be detected by distant observers. This escaped radiation carries away a tiny amount of energy, which must come from somewhere, and that somewhere is the mass energy of the black hole itself. The temperature of Hawking radiation is inversely proportional to the mass of the black hole, meaning that smaller black holes radiate more intensely than larger ones. A black hole with the mass of our Sun would have a temperature of only 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation. Such a black hole would take longer than 1067 years to evaporate completely at time so vast that it makes the current age of the universe seem like an instant. Paradoxically, microscopic black holes, if they exist, would radiate so intensely that they would explode in brilliant flashes of gamma rays. As you settle into sleep tonight, contemplate this gentle cosmic irony, that the universe's most voracious devourers of matter and energy are simultaneously engaged in the most patient act of self-destruction, glowing softly in the darkness as they slowly return their borrowed mass to the cosmos. 12. Cosmic inflation. In the first tiny fraction of a second after the Big Bang, during a period so brief that it defies human comprehension, the universe underwent a phase of expansion so rapid and dramatic that it fundamentally shaped everything we observe in the cosmos today. This is cosmic inflation, a concept that explains not only why the universe appears so uniform in all directions, but also how quantum fluctuations smaller than a proton eventually grew to become the largest structures we can observe. To appreciate the incredible nature of cosmic inflation, consider that this expansion occurred during the first 10 to 32 seconds after the Big Bang, a time interval so short that light could travel only an infinitesimally small distance. During this brief moment, space itself expanded exponentially, growing by a factor of at least 1026 in size. To put this in perspective, imagine a region initially smaller than a proton, suddenly becoming larger than a grapefruit. And this analogy still vastly underestimates the true scale of inflation. The driving force behind cosmic inflation was a hypothetical energy field called the inflaton field, which had the unusual property of causing space to expand at an accelerating rate. Unlike the matter and radiation we observe today, this field created a repulsive gravitational effect that pushed space apart faster and faster. When the inflaton field finally decayed at the end of the inflationary period, it released enormous amounts of energy that heated the universe and created the hot, dense conditions we associate with the traditional Big Bang model. Cosmic inflation solves several puzzles about our universe's structure and properties. It explains why the cosmic microwave background radiation has almost exactly the same temperature in all directions, despite coming from regions that should never have been in thermal contact with each other. The theory also predicts that the universe should be geometrically flat, which matches our observations precisely. Perhaps most remarkably, inflation provides a mechanism for generating the tiny density fluctuations that eventually grew into galaxies and stars. Quantum fluctuations in the inflaton field were stretched by the rapid expansion from subatomic scales to cosmic proportions, creating the seeds of all large-scale structure in the universe. As you drift towards sleep, imagine that brief moment of cosmic inflation, when the entire observable universe was smaller than the period at the end of this sentence, yet already contained within its quantum fluctuations the blueprint for everything that would ever exist. 13 rogue planets. Wandering through the cold depths of interstellar space, unbound by the gravitational embrace of any star, are cosmic orphans known as rogue planets. These solitary worlds drift through the galaxy like interstellar nomads, carrying with them the stories of their violent ejection from their birth systems and the possibility that life might survive in the most unexpected corners of the universe. Rogue planets form through several different mechanisms, each representing a different type of cosmic drama. Some begin their existence like normal planets, condensing from the disk of gas and dust around a young star. However, gravitational interactions with other planets or passing stars can eventually fling these worlds out of their home systems, sending them on lonely journeys through interstellar space at speeds of tens of kilometers per second. Other rogue planets may form independently in space, condensing directly from clouds of gas and dust without ever being associated with a star. These objects occupy the mysterious boundary between planets and brown dwarfs, representing a class of celestial bodies that challenges our traditional definitions of planetary formation. Some of these isolated worlds may be nearly as massive as Jupiter, possessing their own complex atmospheric dynamics and possibly even systems of moons. The number of rogue planets in our galaxy may be staggering. Some estimates suggest there could be billions of these wandering worlds, possibly outnumbering stars themselves. Most remain completely dark and invisible, detectable only when they occasionally pass in front of distant stars, briefly magnifying their light through a phenomenon called gravitational microlensing. Despite their isolation from stellar warmth, some rogue planets might harbor conditions suitable for life. Worlds with thick atmospheres could retain internal heat generated by radioactive decay in their cores, potentially maintaining liquid water beneath protective ice shells. Jupiter-sized rogue planets with large moons might create complex tidal heating systems that could support subsurface oceans for billions of years. These solitary worlds represent some of the most extreme environments where life might potentially exist, completely independent of stellar energy and relying instead on internal heat sources and chemical energy. As you settle into the comfort of your bed tonight, imagine these dark wanderers drifting silently through space, each carrying its own private atmosphere and possibly its own hidden biosphere through the cosmic wilderness. 14. In the theoretical realm where physics meets imagination, there exist hypothetical particles that challenge our most fundamental understanding of cause and effect, space and time. These are tachyon particles that would travel faster than light, and, if they existed, would create paradoxes that might unravel the very fabric of causality itself. The concept of tachyons emerges from Einstein's special theory of relativity, though in a way that Einstein himself never intended. His equations show that as any object with mass approaches the speed of light, its energy requirements approach infinity, making faster-than-light travel impossible for ordinary matter. However, the mathematics also allows for a strange class of particles that would always travel faster than light, never slowing down to light speed or below. For tachyons to exist, they would need to have imaginary mass, not in the sense of being fictional, but in the mathematical sense where their mass would be the square root of a negative number. This gives tachyons their peculiar properties. The faster they move, the less energy they have, and they would lose energy by accelerating rather than gaining it. A tachyon with infinite speed would have zero energy, while a tachyon moving at just slightly above light speed would possess infinite energy. The most disturbing implication of tachyons involves the nature of time itself. Because they travel faster than light, tachyons would appear to move backward in time from the perspective of certain observers. This could theoretically allow information to be sent into the past, creating grandfather paradox-style contradictions that would violate our understanding of cause and effect. Despite extensive searches, no evidence for tachyons has ever been found, and most physicists believe they do not exist in our universe. The mathematical possibility of their existence has instead become a useful tool for exploring the boundaries of physical theory and understanding why nature seems to have built-in protections against violations of causality. As you drift toward sleep tonight, contemplate these ghostly theoretical particles that exist only in the realm of mathematical possibility, forever racing faster than light through equations but apparently banned from the actual cosmos, as if the universe has its own sense of temporal propriety that prevents the past from being changed by messages from the future. 15. Laniakea. Your cosmic address is far more expansive than you might imagine. Beyond your planet, your solar system, and even your galaxy lies a structure so vast that it contains over 100,000 galaxies, arranged across more than 500 million light-years of space. This is Laniakea, the supercluster of galaxies that serves as our cosmic neighborhood and reveals the universe's tendency to organize matter into increasingly magnificent hierarchies. The name Laniakea comes from Hawaiian words meaning immense heaven, and it perfectly captures the scale of this cosmic structure. Discovered only in 2014 through careful mapping of galaxy motions, Laniakea represents a new way of defining cosmic neighborhoods based not on position alone, but on the flow of galaxies through space under the influence of gravity. Traditional methods of defining galactic clusters relied on identifying groups of galaxies that appeared close together in space. However, astronomers realized that a more fundamental approach would be to trace the paths that galaxies follow as they move through space, pulled by gravitational attractions toward regions of higher mass density. These cosmic watersheds define the boundaries of superclusters more accurately than simple proximity. At the heart of Laniakea lies the Great Attractor, the mysterious gravitational anomaly that influences the motion of galaxies across hundreds of millions of light-years. Our Milky Way galaxy sits near one edge of Laniakea, along with our local group of neighboring galaxies, all flowing together toward this central region of enhanced mass density. The discovery of Laniakea has revealed that cosmic structure extends to scales that dwarf individual galaxies. Just as cities are organized into states and countries, galaxies are organized into clusters, clusters into superclusters, and superclusters into even larger structures that may represent the fundamental architecture of the observable universe. Laniakea itself is likely part of even larger structures, possibly connected to other superclusters through tendrils of dark matter and galaxies that span billions of light-years. The universe appears to be organized like a vast cosmic web, with dense filaments of matter surrounding enormous empty voids. As you prepare for sleep tonight, remember that you reside in this immense heaven of galaxies, part of a structure so large that light from its far edges began its journey toward us when the first complex life was just beginning to evolve on Earth. 16. Spaghettification. Picture yourself approaching the edge of a black hole, where one of the universe's most elegantly destructive processes awaits. Spaghettification, also known as the tidal effect, represents the gentle yet inexorable stretching that occurs when gravity becomes overwhelmingly strong. This phenomenon emerges from a fundamental principle of gravitational physics. The closer you are to a massive object, the stronger its gravitational pull becomes. Imagine your body as you drift toward this cosmic giant. The gravitational force pulling on your feet would be significantly stronger than the force acting on your head, creating a differential that stretches you vertically while simultaneously compressing you horizontally. This process unfolds like a cosmic taffy pull, elongating matter in the direction of the gravitational source while squeezing it from the sides. The term spaghettification captures this transformation beautifully. As objects become increasingly thin and elongated, resembling strands of pasta being pulled through space, the tidal forces responsible for this stretching are the same gentle forces that cause ocean tides on Earth, but amplified to extraordinary levels near massive cosmic objects. What makes this phenomenon particularly fascinating is its relationship to the event horizon of black holes. For smaller black holes, spaghettification would occur before you cross this point of no return, stretching you beyond recognition in the vacuum of space. However, with supermassive black holes, their gentler gravitational gradients might allow you to cross the event horizon intact, experiencing spaghettification only as you approach the central singularity. The mathematics behind spaghettification reveals the beautiful precision of Einstein's general relativity. The tidal force follows an inverse cube relationship with distance, meaning that as you get twice as close to the black hole, the stretching force increases by a factor of 8. This exponential relationship explains why the effect becomes so dramatic so quickly. Scientists have observed evidence of spaghettification in stellar material being consumed by black holes, creating spectacular displays of superheated gas streaming in long, luminous tendrils. These cosmic light shows represent matter's final dance before disappearing forever beyond the event horizon, stretching and glowing as it succumbs to gravity's ultimate embrace. 17. Red giants. In the twilight years of stellar evolution, ordinary stars like our Sun undergo one of the most graceful transformations in the cosmos, becoming red giants. This metamorphosis represents a star's response to the fundamental challenge of nuclear fuel depletion, as the hydrogen in its core gradually converts to helium through billions of years of fusion. When a star exhausts the hydrogen fuel in its core, the delicate balance between gravitational collapse and radiation pressure begins to shift. The core, now primarily composed of helium, contracts under its own gravity, becoming denser and hotter. This contraction releases gravitational energy, heating the surrounding shell of remaining hydrogen to temperatures sufficient for nuclear fusion. The hydrogen shell burns more vigorously than the original core ever did, producing enormous amounts of energy that push against the star's outer layers. Like a gentle cosmic breath, this energy inflates the star's outer envelope to incredible proportions. Our Sun, when it becomes a red giant in approximately 5 billion years, will expand to roughly 100 times its current size, potentially engulfing the orbits of Mercury and Venus. The surface of a red giant cools as it expands, giving these stellar giants their characteristic ruddy hue. The same physics that makes a piece of metal glow red when moderately heated applies here. With surface temperatures dropping to around 3000 Kelvin compared to the Sun's current surface temperature of nearly 6000 Kelvin, red giants pulsate gently, breathing in and out over periods ranging from months to years. These pulsations occur because the expanded outer layers become only loosely bound to the star, creating instabilities that cause the entire stellar atmosphere to oscillate. During these pulsations, red giants shed material into space, creating beautiful planetary nebulae that enrich the interstellar medium with heavy elements forged in stellar cores. This phase of stellar evolution lasts for millions of years, a brief moment in cosmic terms, but long enough to fundamentally alter the star's surrounding environment. The increased luminosity of red giants can warm previously frozen worlds, potentially creating new habitable zones in solar systems while simultaneously destroying inner planets through tidal forces and intense radiation. 18. Virtual particles. In the quantum realm that underlies all reality, empty space teems with ghostly entities called virtual particles, flickering in and out of existence in time frames so brief they challenge our understanding of what it means to exist. These ephemeral quantum fluctuations represent one of the most profound insights of modern physics, revealing that what we perceive as empty vacuum actually bubbles with constant activity. Virtual particles emerge from the fundamental uncertainty principle of quantum mechanics. which states that energy and time cannot both be precisely known simultaneously. This uncertainty creates a cosmic loophole that allows particle pairs to spontaneously appear from nothing, borrowing energy from the vacuum itself. However, this borrowed energy must be repaid quickly, causing the particle pairs to annihilate each other and return to nothingness within incredibly short time frames. The lifetime of these virtual particles depends on their energy through Heisenberg's uncertainty relation. More energetic virtual particles exist for shorter periods, while less energetic ones can persist slightly longer. Even the most long-lived virtual particles exist for only minuscule fractions of a second, making them impossible to observe directly. Yet their effects permeate every aspect of physical reality. Virtual particles mediate all fundamental forces in nature. When you feel the electromagnetic repulsion between two magnets, virtual photons carry that force between them. The strong nuclear force that binds protons and neutrons in atomic nuclei operates through virtual gluons, while the weak nuclear force responsible for certain types of radioactive decay involves virtual W and Z bosons. Even gravity, according to quantum field theory, should involve virtual gravitons. Though these remain theoretical, the Casimir effect provides compelling experimental evidence for virtual particles. When two metal plates are placed extremely close together in a vacuum, they experience an attractive force caused by virtual particles. The space between the plates restricts which virtual particles can exist there, while the surrounding vacuum contains the full spectrum of quantum fluctuations. This imbalance creates a pressure that pushes the plates together, demonstrating the reality of virtual particle interactions. These quantum fluctuations also played a crucial role in cosmic inflation, the rapid expansion of the early universe. Virtual particles provided the seed fluctuations that eventually grew into the large-scale structure of galaxies and galaxy clusters we observe today. 19 Boats, Void. In the constellation Boats lies one of the most profound mysteries of cosmic architecture, a spherical region of space so empty that it challenges our understanding of how the universe organized itself after the Big Bang. Known as the Boat's Void, or sometimes called the Great Nothing, this cosmic bubble spans approximately 330 million light-years in diameter, containing virtually no galaxies in a volume where thousands should exist. To appreciate the extraordinary emptiness of this region, consider that a typical volume of space this size should contain around 2,000 galaxies. Instead, the Boat's Void contains fewer than 60 galaxies, most of which cluster around its edges, like pearls on the rim of an enormous invisible sphere. This represents an underabundance of matter, so severe that the probability of such a void forming through random chance approaches zero. The discovery of this cosmic emptiness came through painstaking galaxy surveys in the 1970s and 80s, when astronomers mapping the three-dimensional structure of the universe noticed a peculiar absence of light sources in this direction. As more sensitive telescopes probed deeper into this region, the void's true scale became apparent, revealing a spherical emptiness that spans nearly 1% of the observable universe's diameter. The existence of such voids provides crucial insights into cosmic evolution and the distribution of dark matter. Computer simulations of cosmic structure formation suggest that voids like boats form naturally as matter gravitates toward dense regions, leaving behind increasingly empty spaces. However, the sheer size and spherical symmetry of the boat's void push these models to their limits, suggesting that our understanding of cosmic evolution may be incomplete. Within this vast emptiness, space itself expands faster than in denser regions of the universe. The lack of gravitational anchors means that the fabric of space-time stretches more freely, creating an accelerated expansion that makes the void grow larger over time. Any matter that might wander into this region gets swept along by this expansion, maintaining the void's emptiness. The few galaxies that do exist within the boat's void appear to be moving away from the center at high speeds, as if fleeing from some cosmic repulsion. These galaxies tend to be smaller and less massive than typical galaxies, perhaps stripped of material by their journey through this cosmic desert. 20. The cosmic web. Stretching across billions of light-years, the largest structures in the universe form an intricate tapestry known as the cosmic web, a vast network of dark matter filaments that connects galaxies and galaxy clusters in an architecture that resembles neural networks or biological systems. This cosmic scaffolding represents the fundamental organizing principle of the universe, determining where galaxies form and how they evolve over cosmic time. The cosmic web emerged from tiny quantum fluctuations in the early universe, microscopic variations in density that existed when the cosmos was less than a second old. As the universe expanded and cooled, these primordial ripples grew under their own gravity, eventually becoming the seeds of cosmic structure. Dark matter, which interacts only through gravity, began to collapse into dense nodes connected by tenuous filaments, creating a three-dimensional network that spans the observable universe. Ordinary matter, comprising stars, planets, and everything we can see, represents only about 5% of the universe's total mass energy. This visible matter follows the gravitational pathways carved out by dark matter, flowing along the cosmic web's filaments like water following riverbeds. Where these streams converge at the web's nodes, galaxies cluster together in some of the most massive structures in the universe. The filaments of the cosmic web stretch for hundreds of millions of light-years, yet they are remarkably thin, often only a few million light-years in diameter. Along these tendrils, galaxies arrange themselves like beads on cosmic strings, connected by streams of hot gas that glow faintly in X-ray wavelengths. This intergalactic medium serves as a reservoir of material that continues to feed star formation in galaxies throughout cosmic history. Between the filaments lie enormous voids, regions of space so empty they contain almost no matter at all. These cosmic deserts represent the spaces between the web's structure, vast spherical regions where galaxies are rare and space expands faster than average. The contrast between the dense filaments and empty voids creates a foam-like structure that characterizes the universe on its largest scales. Modern supercomputer simulations can model the formation and evolution of the cosmic web with remarkable accuracy, tracing the growth of structure from the early universe to the present day. These simulations reveal that the web continues to evolve, with matter flowing along filaments toward the largest galaxy clusters, gradually building up the most massive structures in the universe, while the voids grow larger and emptier. 21. White holes. In the theoretical landscape of Einstein's general relativity exists one of the most enigmatic and speculative objects in cosmology: white holes, the hypothetical opposite of black holes that would spew matter and energy outward with such violence that nothing could ever approach or enter them. While black holes consume everything that crosses their event horizon, white holes would represent regions of spacetime that violently reject all matter and energy, creating a cosmic fountain that pours material into the universe. The mathematics of general relativity that predicts black holes also allows for these reverse solutions, where the equations describe objects with event horizons that work in the opposite direction. Instead of an inward point of no return, white holes would possess outward event horizons, boundaries beyond which no information or matter could travel inward. Any object attempting to approach a white hole would find itself swept away by the tremendous outflow of energy and material. White holes would violate the second law of thermodynamics in spectacular fashion, appearing to create order and structure from nothing while decreasing entropy in their vicinity. This fundamental problem has led most physicists to conclude that white holes, while mathematically possible, cannot exist in the real universe. The arrow of time and the inexorable increase of entropy seem to forbid such objects from forming or persisting. However, some theoretical physicists have proposed that white holes might explain certain astronomical phenomena that remained mysterious. Gamma ray bursts, the most energetic explosions in the universe after the Big Bang, release tremendous amounts of energy in short periods that challenge conventional explanations. Could these represent the brief formation and immediate destruction of white holes, creating cosmic fountains that blast energy across the universe before quickly disappearing? The Big Bang itself bears some resemblance to a white hole event, representing the ultimate outpouring of matter and energy from what appears to be a single point. Some cosmological models suggest that our entire universe might represent the interior of a white hole, with the Big Bang marking the moment when this cosmic geyser began its eternal outflow of space-time and matter. If white holes could exist, they would create fascinating paradoxes. Time dilation near these objects would work in reverse compared to black holes, with distant observers seeing events near the white hole occurring in slow motion. The ergosphere of a rotating white hole would fling objects away at incredible speeds, making any approach impossible regardless of the technology employed. 22. The Big Bang. Approximately 13.8 billion years ago, Everything that exists today emerged from an incomprehensibly hot and dense state in an event we call the Big Bang, the moment when time, space, matter, and energy began their cosmic dance. This singularity represents not an explosion in space, but rather the explosive expansion of space itself, carrying matter and energy along as the universe underwent its first moments of existence. In the earliest fraction of a second, when the universe was smaller than an atom, temperatures exceeded 10 to the 32nd power, Kelvin, conditions so extreme that the fundamental forces of nature unified into a single superforce. During this primordial epoch, the universe expanded faster than the speed of light through a process called cosmic inflation, stretching quantum fluctuations to macroscopic scales and setting the stage for all future cosmic structure. As the universe expanded, it cooled rapidly, allowing the unified forces to separate into the distinct fundamental interactions we observe today. First, gravity separated from the other forces, followed by the strong nuclear force, and finally the electromagnetic and weak nuclear forces split apart. These phase transitions released enormous amounts of energy, driving further expansion and cooling of the primordial cosmos. The first stable particles formed when the universe was about 1 second old and had cooled to roughly 10 billion Kelvin. Protons and neutrons condensed from the primordial quark soup, establishing the building blocks of atomic nuclei. During the next few minutes, a process called Big Bang nucleosynthesis forged the first light elements, creating roughly 75% hydrogen and 25% helium, along with trace amounts of lithium and beryllium. For the next 380,000 years, the universe remained opaque to light, filled with a hot plasma of ions and electrons. When temperatures finally dropped to about 3000 Kelvin, electrons combined with nuclei to form the first neutral atoms in an event called recombination. This cosmic clearing allowed light to travel freely for the first time, creating the cosmic microwave background radiation that we still detect today as the afterglow of the Big Bang. The tiny temperature fluctuations in this ancient light revealed the seeds of cosmic structure, microscopic variations in density that would eventually grow under gravity to become galaxies, stars, and planets. These primordial ripples, stretched to cosmic proportions by inflation, provide our best window into the conditions that existed when the universe was less than a day old. 23. Binary star systems. More than half of all stars in the universe share their cosmic dance with stellar companions, locked in gravitational embrace as binary star systems that can persist for billions of years. These stellar partnerships represent some of the most dynamic and beautiful phenomena in astronomy, creating cosmic laboratories where extreme physics plays out across vast scales of space and time. Binary stars form through several different processes during stellar birth. Most commonly, they emerge from the same molecular cloud, where gravitational instabilities cause the collapsing gas to fragment into multiple dense cores. These stellar embryos, born from the same cosmic material, begin their lives in orbital motion around their common center of mass, establishing gravitational bonds that can endure throughout their stellar lifetimes. The orbital periods of binary systems span an enormous range, from contact binaries that complete their dance in less than a day to wide binaries with periods measured in millions of years. Close binary systems create some of the most spectacular displays in the universe, with stellar material streaming between the two stars in luminous arcs of superheated gas. These mass transfer events can dramatically alter stellar evolution, causing stars to gain or lose significant amounts of material over time. When binary stars have significantly different masses, their evolution becomes a complex interplay of stellar life cycles. The more massive star evolves faster, expanding into a red giant, while its companion remains on the main sequence. If the stars orbit closely enough, the expanding giant can overflow its gravitational boundary, called the Roche lobe, transferring material to its companion and potentially creating explosive phenomena. Type Ia supernova, among the most important cosmic distance markers, result from binary evolution. When a white dwarf star accumulates material from its companion until it reaches a critical mass threshold, it undergoes a thermonuclear explosion of extraordinary violence. These cosmic bombs achieve nearly identical peak luminosities, making them invaluable tools for measuring cosmic distances and studying the expansion of the universe. Eclipsing binary systems provide astronomers with precise measurements of stellar properties, When the orbital plane aligns with Earth, we observe periodic dimming as one star passes in front of the other. By analyzing these light curves, astronomers can determine stellar masses, radii, and surface temperatures with remarkable precision, providing fundamental data for understanding stellar physics and evolution. Gravitational wave detectors have revealed that merging binary black holes and neutron stars create ripples in spacetime itself, opening an entirely new window for studying these cosmic partnerships. 24. Ixion. In the deepest mysteries of particle physics lies a hypothetical particle called the axion, proposed to solve one of the most perplexing problems in our understanding of the fundamental forces, while potentially explaining the invisible dark matter that comprises most of the universe's mass. These ghostly particles, if they exist, would be among the lightest and most weakly interacting constituents of reality, permeating all of space in quantities that dwarf ordinary matter. The axion emerged from theoretical attempts to resolve the strong CP problem, a puzzle about why the strong nuclear force appears to respect certain symmetries that it should, according to quantum field theory, violate significantly. The equations governing the strong force contain terms that would cause neutrons to possess electric dipole moments. Yet experimental searches have found no evidence of such asymmetries. The axion provides an elegant solution by introducing a new field that dynamically cancels these problematic terms. These theoretical particles would possess extraordinary properties that make them nearly impossible to detect directly. Axions would have masses millions of times smaller than electrons, interacting so weakly with ordinary matter that trillions could pass through your body every second without leaving any trace. Their primary interaction with normal matter would occur through their coupling to electromagnetic fields, occasionally converting into photons under specific conditions involving strong magnetic fields. The cosmological implications of axions are profound. If these particles exist, they would have been produced in enormous quantities during the early universe, when temperatures and energies were sufficient to create them through various mechanisms. As the universe expanded and cooled, these primordial axions would have become the dominant form of matter, clustering gravitationally to form the dark matter halos that surround galaxies. Unlike ordinary matter, axions would form a different type of dark matter called cold dark matter, moving slowly compared to the speed of light and clumping together on large scales. This behavior matches observations of cosmic structure formation better than many other dark matter candidates, making axions particularly attractive to cosmologists studying the evolution of the universe. Several experimental efforts worldwide are attempting to detect axions through their predicted conversion to photons in strong magnetic fields. These experiments, with names like DMX and CAST, represent some of the most sensitive searches for new physics ever attempted, probing parameter spaces that could reveal evidence for these elusive particles, and potentially solve two of physics' greatest mysteries simultaneously. 25. Tidal forces. The same gravitational phenomenon that creates the rhythmic rise and fall of Earth's oceans operates throughout the cosmos on scales, ranging from planetary rings to galactic interactions, manifesting as tidal forces that shape the architecture of the universe through gentle but inexorable differential gravitational attraction. These forces arise whenever the gravitational field strength varies significantly across the extent of an object, creating stretching and compressing effects that can be both creative and destructive. Tidal forces emerge from the inverse square law of gravity, which dictates that gravitational attraction weakens rapidly with distance. When a celestial body experiences the gravitational pull of a massive neighbor, the side closer to the massive object feels a stronger gravitational tug than the far side. This difference in gravitational acceleration creates internal stresses that can deform, stretch, or even completely disrupt the affected body. On Earth, the Moon's gravity creates tidal bulges in our oceans, with water on the side facing the Moon pulled more strongly toward our satellite than the solid Earth beneath it. Simultaneously, water on the opposite side of Earth experiences weaker lunar gravity than the planet's center, creating a second tidal bulge. As Earth rotates beneath these bulges, coastal regions experience the familiar cycle of high and low tides that has influenced human civilization for millennia. The Sun also contributes to Earth's tides, though less significantly than the Moon due to its greater distance. When the Sun and Moon align during new and full moons, their tidal effects combine to create spring tides with exceptional high and low water levels. When they work at cross purposes during quarter moons, the result is neppy tides with more moderate tidal ranges. Throughout the solar system, tidal forces sculpt the surfaces and interiors of moons and planets. Jupiter's immense gravity creates powerful tides on its moon, Io, stretching and compressing the rocky interior to such an extent that friction generates enough heat to drive constant volcanic activity. Europa experiences similar tidal heating that maintains a liquid ocean beneath its icy surface, creating one of the most promising environments for extraterrestrial life in our solar system. Tidal forces also explain the formation of planetary ring systems, where material orbiting too close to a massive planet gets stretched beyond its ability to hold together gravitationally. The Roche limit defines this critical distance, inside which tidal forces overcome the self-gravity of orbiting objects, preventing moons from forming and destroying any that venture too close. 26. Primordial black holes. In the chaotic first moments after the Big Bang, when the universe contained regions of extreme density variation, theoretical physics suggests that some areas of space collapsed directly into black holes without ever forming stars, creating primordial black holes that could range in mass from microscopic to stellar scales. These ancient objects represent fossils from the earliest epoch of cosmic history, potentially offering unique insights into the conditions that existed when the universe was less than a second old. Unlike stellar black holes that form from the collapse of massive stars, primordial black holes would have condensed directly from the primordial density fluctuations present in the early universe. During the radiation-dominated era, before atoms formed, regions where matter density exceeded the critical threshold could undergo gravitational collapse, creating black holes with masses determined by the cosmic horizon size at the time of formation. The mass spectrum of primordial black holes spans an extraordinary range. Those forming in the first fraction of a second after the Big Bang would have masses comparable to asteroids or mountains, while black holes forming later could achieve masses similar to stars or even larger structures. This diversity makes primordial black holes fascinating candidates for explaining several mysterious aspects of modern cosmology. Small primordial black holes would behave very differently from their stellar cousins. Due to a quantum mechanical effect discovered by Stephen Hawking, black holes emit radiation at a rate inversely proportional to their mass, meaning that microscopic black holes would glow brightly and evaporate rapidly through Hawking radiation. The smallest primordial black holes would have completely evaporated by now, potentially contributing to the gamma-ray background that permeates space. However, primordial black holes with masses above approximately 10 to the 15th grams would still exist today, having evaporation times longer than the age of the universe. These survivors could comprise some or all of the mysterious dark matter that dominates cosmic structure formation, offering a solution to one of cosmology's greatest puzzles without requiring exotic new particles. Recent gravitational wave detections of merging black holes have renewed interest in primordial black holes as potential sources of these signals. Some of the black hole mergers observed by LIGO and Virgo involve masses that are difficult to explain through stellar evolution, possibly indicating a primordial origin for at least some of these objects. The search for primordial black holes continues through multiple observational channels, from gravitational lensing effects to searches for their evaporation signatures, potentially revealing these ancient relics from the universe's violent birth. 27. The Fermi Paradox. In 1950, physicist Enrico Fermi posed a deceptively simple question that has haunted scientists for decades. If the universe teems with potentially habitable worlds and intelligent life should be common, where is everybody? This profound puzzle, known as the Fermi Paradox, highlights the apparent contradiction between high estimates for the probability of extraterrestrial intelligence and the complete absence of evidence for such civilizations despite decades of searching. The paradox begins with seemingly reasonable assumptions about cosmic abundance and evolution. Our galaxy contains hundreds of billions of stars, many with planetary systems that include worlds in habitable zones where liquid water could exist. Given the age of the Milky Way, approximately 13 billion years, there has been ample time for life to evolve, develop intelligence, and spread across vast regions of space through interstellar colonization or communication. Conservative estimates suggest that even if intelligent civilizations arise rarely and spread slowly, the galaxy should show obvious signs of their presence. Advanced civilizations might construct massive engineering projects visible across interstellar distances, emit characteristic signatures from their technology, or, at minimum, respond to the radio signals that Earth has been broadcasting into space for nearly a century. Yet our searches have yielded only silence. The search for extraterrestrial intelligence has monitored millions of stars across multiple wavelengths without detecting any clearly artificial signals. Space telescopes have found no evidence of stellar engineering projects or other signs of cosmic-scale civilization. Even our own solar system shows no trace of visitation or monitoring by extraterrestrial intelligence, despite billions of years during which such contact could have occurred. Proposed solutions to the Fermi paradox range from the optimistic to the sobering. Perhaps intelligent life is indeed rare, requiring an improbable sequence of evolutionary accidents that occurred on Earth but seldom elsewhere. The development of complex multicellular life took billions of years on our planet, and the emergence of technological intelligence happened only recently in cosmic terms. Alternatively, advanced civilizations might exist but remain undetectable to our current technology. They could communicate through means we have not yet discovered, engineer their environments in ways we cannot recognize, or deliberately avoid contact with younger civilizations like ourselves. The vast scales of space and time might make contact between civilizations extraordinarily improbable despite their existence. More concerning possibilities suggest that technological civilizations tend to destroy themselves or face insurmountable challenges that prevent their long-term survival and expansion throughout the galaxy.
28. Wolf-Rayet stars. Among the most massive and spectacular stars in the universe, Wolf-Rayet stars represent the final blazing chapter in the lives of the largest stellar giants, burning through their remaining nuclear fuel at prodigious rates while casting off their outer layers in powerful stellar winds that can reach speeds of several thousand kilometers per second. These cosmic furnaces shine with luminosities hundreds of thousands of times greater than our Sun, creating some of the most extreme environments in the galaxy. Wolf-Rayet stars begin their lives as massive main-sequence stars with initial masses exceeding 25 times that of the Sun. These stellar behemoths burn through their hydrogen fuel much more rapidly than ordinary stars, completing their main-sequence lifetimes in just a few million years compared to the billions of years that lower-mass stars enjoy. As they evolve beyond the main sequence, these massive stars develop complex internal structures with multiple nuclear burning shells. The defining characteristic of Wolf-Rayet stars is their powerful stellar winds, which strip away the star's outer hydrogen envelope to reveal the nuclear-processed interior. These winds, driven by radiation pressure from the incredibly luminous stellar core, can remove several Earth masses of material every year. The exposed surface reveals the products of nuclear fusion: helium, carbon, nitrogen, and oxygen that were forged in the star's interior through the CNO cycle and helium-burning processes. Astronomers classify Wolf-Rayet stars based on the dominant elements visible in their spectra. WN stars show strong nitrogen lines, indicating exposure of CNO-processed material, while WC stars display carbon and oxygen features characteristic of helium-burning products. A third category, WO stars, represents the most evolved examples, with oxygen-dominated spectra, revealing the deepest layers of nuclear processing. The stellar winds from Wolf-Rayet stars create spectacular nebulae as the high-speed gas collides with previously ejected material or surrounding interstellar medium. These wind-blown bubbles can extend for many light years around the central star, glowing brilliantly in the light of ionizing ultraviolet radiation. The mechanical energy of these winds also triggers star formation in nearby molecular clouds, making Wolf-Rayet stars important agents of galactic chemical and dynamical evolution. Wolf-Rayet stars are among the primary candidates for producing Type IC supernova, core collapse explosions that occur when massive stars exhaust their nuclear fuel. Some Wolf-Rayet stars may also be progenitors of long-duration gamma-ray bursts, the most energetic explosions in the universe, when they form rotating black holes during their final collapse. 29. Quantum foam. At the smallest conceivable scales of space and time, where distances shrink to the Planck length of 10 to the negative 35 meters and durations compressed to the Planck time of 10 to the negative 44 seconds, the smooth fabric of space-time that we experience in everyday life becomes a seething, chaotic landscape known as quantum foam. This theoretical structure represents the ultimate marriage of quantum mechanics and general relativity, where the certainty of classical physics dissolves into probabilistic fluctuations that constantly create and destroy virtual particles and even tiny wormholes. Quantum foam emerges from the Heisenberg uncertainty principle applied to spacetime itself. Just as particles cannot have precisely defined positions and momenta simultaneously, the geometry of space and time cannot be perfectly smooth and well-defined at the smallest scales. Instead, spacetime becomes subject to quantum fluctuations that cause its structure to writhe and bubble like foam on the ocean's surface. These fluctuations occur on scales so small that they lie far beyond the reach of any conceivable experiment. To probe the Planck scale would require energies equivalent to the entire mass energy of a proton concentrated into a region smaller than an atomic nucleus, conditions that exist nowhere in the current universe except possibly in the hearts of black holes or during the earliest moments after the Big Bang. At this fundamental level, the familiar concepts of distance and duration lose their meaning. Space and time become quantized, breaking down into discrete units that represent the smallest possible measurements. The smooth continuum of Einstein's spacetime gives way to a granular structure where the geometry of space undergoes constant quantum fluctuations, creating temporary distortions that pop into existence and disappear faster than light could cross them. Virtual particles that normally populate empty space according to quantum field theory become even more exotic in the quantum foam regime. Pairs of particles and antiparticles spontaneously materialize from pure geometry, borrowing energy from the curvature of spacetime itself. These virtual particles exist for such brief moments that they cannot be observed directly, yet they contribute to the vacuum energy density that drives cosmic expansion. Some theories suggest that quantum foam might contain microscopic wormholes, tiny tunnels through spacetime that connect distant regions of the universe. These quantum wormholes would constantly appear and disappear, creating a frothy topology where space becomes multiply connected on the smallest scales. While these structures would be far too small and short-lived to allow macroscopic travel, they might play important roles in the fundamental physics of spacetime. 30. Solar wind. Streaming outward from our sun at speeds reaching 800 kilometers per second, an invisible river of charged particles called the solar wind carries the solar atmosphere throughout the entire solar system, creating a vast magnetic bubble called the heliosphere that extends far beyond the orbit of Pluto. This continuous outflow of plasma represents the sun's breath, a stellar exhalation that has blown steadily for billions of years and shapes the space environment around every planet in our cosmic neighborhood. The solar wind originates in the sun's corona, the million-degree outer atmosphere that extends far above the visible solar surface. At these extreme temperatures, hydrogen atoms become completely ionized, creating a plasma of free protons and electrons. The intense heat provides these particles with enough energy to escape the sun's gravitational pull, accelerating them to supersonic speeds as they race away from our star. Two distinct types of solar wind flow from different regions of the solar corona. Fast wind streams from coronal holes, areas where the sun's magnetic field lines extend directly into space rather than looping back to the surface. These regions appear dark in X-ray images because their lower density and temperature allow hot plasma to escape freely. Slow wind emanates from the boundaries of closed magnetic field regions, where plasma gradually leaks out along magnetic field lines that eventually open into interplanetary space. As the solar wind expands through the solar system, it carries with it the sun's magnetic field, creating the interplanetary magnetic field that permeates the space between planets. This frozen-in magnetic field rotates with the sun, creating a spiral pattern called the Parker spiral as the outflowing plasma maintains its connection to the solar surface while the sun spins beneath it. The interaction between solar wind and planetary magnetospheres creates some of nature's most beautiful displays. When Earth's magnetic field deflects solar wind particles toward the polar regions, they collide with atmospheric molecules to produce auroras, the northern and southern lights that have inspired human imagination for millennia. Other planets with magnetic fields experience similar phenomena, creating auroral displays on Jupiter, Saturn, and other worlds. Solar wind also poses challenges for space exploration and technology. During periods of high solar activity, enhanced solar wind can damage satellites, disrupt radio communications, and pose radiation hazards to astronauts. The Apollo missions had to be timed carefully to avoid major solar storms that could have endangered crew members. Traveling beyond Earth's protective magnetosphere. The heliosphere created by solar wind serves as our solar system's cosmic shield, partially deflecting galactic cosmic rays that would otherwise penetrate more deeply into planetary atmospheres.
31. Supermassive black holes. At the heart of nearly every large galaxy in the universe, including our own Milky Way, lurk gravitational monsters of unimaginable proportions known as supermassive black holes. Cosmic entities containing the mass of millions or billions of suns, compressed into regions smaller than our solar system. These galactic anchors represent some of the most extreme objects in the universe, wielding gravitational influence that shapes the evolution of entire galaxies across billions of years. Unlike their stellar mass cousins that form from collapsing stars, supermassive black holes present astronomers with a profound mystery regarding their origin and growth. These giants contain far too much mass to have formed through simple stellar collapse, and they appear to have existed when the universe was very young, less than 1 billion years after the Big Bang. This early appearance suggests that supermassive black holes either formed through exotic processes in the primordial universe or grew with extraordinary efficiency during the cosmos' youth. Current theories propose several formation mechanisms for these galactic giants. Direct collapse scenarios suggest that massive gas clouds in the early universe could have collapsed directly into intermediate mass, black holes weighing tens of thousands of solar masses, providing seeds that could grow rapidly through accretion. Alternative models propose that the first generation of massive stars, weighing hundreds of times more than our Sun, could have collapsed to form intermediate seeds that later merged and accreted material to become supermassive. The growth phase of supermassive black holes creates some of the most luminous objects in the universe. When matter spirals into these gravitational wells, friction and magnetic forces heat the infalling material to temperatures of millions of degrees, causing it to glow brilliantly across the electromagnetic spectrum. This process powers quasars' active galactic nuclei that can outshine their entire host galaxies and remain visible across cosmic distances exceeding 13 billion light. The relationship between supermassive black holes and their host galaxies appears to be one of cosmic symbiosis. The mass of the central black hole correlates remarkably well with properties of the galactic bulge, suggesting that these objects co-evolve through feedback mechanisms that regulate both black hole growth and star formation. When actively feeding, supermassive black holes generate powerful jets of particles and energy that can heat the surrounding gas, temporarily halting star formation and their own growth in a self-regulating cycle. The supermassive black hole at the center of our galaxy, known as Sagittarius A*, contains approximately 4 million solar masses, within a region about 17 times the diameter of our Sun. This relatively quiet giant occasionally flares with increased luminosity when small amounts of gas fall into its gravitational grasp, providing astronomers with opportunities to study the physics of matter under extreme gravitational conditions. Recent advances in telescope technology have enabled direct imaging of the event horizons of supermassive black holes, confirming Einstein's predictions about the behavior of spacetime near these cosmic extremes and opening new windows for studying the fundamental nature of gravity itself. 32. The heat death. In the far distant future, countless trillions of years from now, the universe may reach a state of maximum entropy known as heat death, a cosmic finale where all energy becomes evenly distributed throughout space, and no further work can be performed. This ultimate fate represents the logical conclusion of the second law of thermodynamics applied to the cosmos as a whole, painting a picture of a universe that gradually winds down like a cosmic clock running out of energy. The concept of heat death emerges from the fundamental principle that entropy, a measure of disorder or randomness, always increases in isolated systems. As the universe expands and cools, energy spreads out more evenly, and temperature differences that drive all cosmic processes gradually diminish. Stars will exhaust their nuclear fuel, galaxies will drift apart due to cosmic expansion, and even black holes will eventually evaporate through Hawking radiation, leaving behind a cold, dark cosmos filled only with elementary particles. This cosmic endgame unfolds over timescales that dwarf human comprehension. The current era of stellar nucleosynthesis, when stars shine brightly and create heavy elements, represents merely the opening chapter of cosmic history. In about 100 trillion years, the last red dwarf stars will exhaust their hydrogen fuel and fade to darkness. Galaxies will lose their remaining stars through gravitational interactions, flinging them into intergalactic space or feeding them to central black holes. Even after the last stars die, the universe will continue evolving through increasingly exotic processes. Protons themselves may decay over timescales of 10 to the 34th years, dissolving the atomic nuclei that form the foundation of matter. Black holes will slowly evaporate through quantum processes, with supermassive black holes taking approximately 10 to the 100 years to completely disappear. The final remnants will be elementary particles scattered across an ever-expanding cosmos approaching absolute zero temperature. Yet heat death does not represent the complete cessation of all activity. Even in this ultimate state, quantum fluctuations would continue, occasionally creating temporary pockets of organization through purely random processes. Given infinite time, these fluctuations could theoretically recreate any configuration of matter, including intelligent observers, though such events would occur over timescales so vast that they defy meaningful description. Some theories suggest alternatives to heat death that could rejuvenate the universe. If dark energy behaves differently than currently understood, cosmic expansion might reverse, leading to a big crunch that could restart the cosmic cycle. Other models propose that quantum tunneling could create new universes from the vacuum, providing escape routes from thermal equilibrium. The heat death scenario also assumes that our current understanding of physics remains valid over these extreme timescales. New discoveries in fundamental physics could reveal processes that prevent or reverse the increase in entropy, potentially allowing the universe to maintain organization and complexity indefinitely. Despite its seemingly bleak implications, heat death represents the logical culmination of physical laws that have operated successfully throughout cosmic history, reminding us that even the universe itself follows the same thermodynamic principles that govern everyday processes on Earth. 33. Planetary nebulae. Among the most beautiful and ethereal objects in the night sky, planetary nebulae represent the artistic final acts of dying stars, creating luminous sculptures of gas and dust that glow with jewel-like colors across space for thousands of years. These cosmic artworks have nothing to do with planets despite their name, which arose because early telescopic observers thought they resembled the greenish disks of distant planets like Uranus and Neptune. Planetary nebulae form during the final evolutionary stages of stars, with masses similar to our Sun, typically ranging from 1 to 8 solar masses. As these stars age and exhaust the hydrogen fuel in their cores, they expand to become red giants, puffing their outer atmospheric layers into space through increasingly powerful stellar winds. This mass loss process accelerates during the star's final millennia, creating an expanding shell of gas surrounding the hot, dense core that remains behind. The transformation from red giant to planetary nebula occurs when the central star becomes hot enough to ionize the surrounding gas shell. With surface temperatures reaching 50,000 to 200,000 Kelvin, the exposed stellar core emits intense ultraviolet radiation that strips electrons from atoms in the expanding gas cloud. These ionized atoms then recombine with electrons, emitting characteristic wavelengths of light that create the nebula's spectacular colors. The diverse shapes and structures of planetary nebulae reflect the complex physics of stellar death and the influence of magnetic fields, binary companions, and rotation on the mass ejection process. Simple spherical shells form when mass loss occurs uniformly in all directions, while bipolar nebulae with their distinctive hourglass or butterfly shapes arise when stellar rotation or binary interactions focus the outflowing gas into jets along the star's rotational axis. The colors that make planetary nebulae so visually striking result from specific atomic transitions in the ionized gas. Hydrogen produces red and blue emission lines, while doubly ionized oxygen creates the characteristic blue-green glow that dominates many nebulae. Nitrogen contributes red emission lines, and other trace elements add subtle hues that reveal the chemical composition of the stellar material being recycled into space. Central to each planetary nebula lies a white dwarf star, the hot, dense remnant of the original star's core. These stellar corpses contain about half the mass of the original star, compressed into an object roughly the size of Earth. White dwarfs cool slowly over billions of years, gradually fading as they radiate away their stored thermal energy. During their hottest phases, they provide the energy source that illuminates the surrounding nebula. Planetary nebulae serve as crucial agents of cosmic recycling, returning processed stellar material to the interstellar medium where it can be incorporated into future generations of stars and planets. The gas expelled during planetary nebula formation carries elements like carbon, nitrogen, and oxygen that were created through nuclear fusion in the star's interior, enriching the galaxy with the building blocks necessary for rocky planets and biological processes. These cosmic sculptures remain visible for only 10 to 50,000 years before the expanding gas becomes too dilute to glow brightly. making them relatively brief phenomena in astronomical terms, but among the most photogenic objects, accessible to both professional astronomers and amateur stargazers exploring the night sky. 34. Deep within the mathematical frameworks of modern physics lurk theoretical particles called magnetic monopoles, hypothetical objects that would possess isolated north or south magnetic poles, without the opposing partner that characterizes all known magnets. While every magnet we encounter in daily life has both north and south poles connected by invisible field lines, monopoles would represent magnetic charges existing independently in space, creating radial magnetic fields similar to the electric fields surrounding charged particles. The theoretical foundation for magnetic monopoles emerges from the elegant symmetry principles that govern fundamental physics. Just as electric charges can exist as isolated positive or negative entities, mathematical consistency suggests that magnetic charges should also be possible. James Clerk Maxwell's equations of electromagnetism, which describe the relationship between electric and magnetic fields, become more symmetric and aesthetically pleasing when modified to include magnetic monopoles alongside electric charges. Paul Dirac made a profound discovery in 1931 when he demonstrated that the existence of even a single magnetic monopole anywhere in the universe would automatically quantize electric charge, explaining why electric charge always appears in discrete multiples of the electron's charge. This theoretical result suggests that monopoles might be fundamentally necessary for the mathematical consistency of electromagnetism, even if they remain undetected. Grand unified theories, which attempt to unify the electromagnetic, weak, and strong nuclear forces into a single framework, predict that magnetic monopoles should have formed abundantly during the extremely high-energy conditions that existed in the first fraction of a second after the Big Bang. These primordial monopoles would be incredibly massive, potentially weighing as much as entire atomic nuclei, while being smaller than protons, making them extraordinarily dense and difficult to create or detect. The scarcity or complete absence of observable monopoles in the current universe presents theoretical physicists with a significant puzzle. If grand unified theories correctly describe nature, monopoles should exist in sufficient numbers to be detectable. Yet decades of sophisticated searches have yielded no confirmed discoveries. This monopole problem represents one of the motivations for inflationary cosmology, which proposes that rapid cosmic expansion in the early universe diluted the monopole density to undetectable levels. Experimental searches for magnetic monopoles have employed increasingly sensitive techniques to detect their distinctive signatures. Monopoles would interact with magnetic fields in ways that differ dramatically from ordinary particles, creating characteristic patterns in particle detectors and generating unique electromagnetic signals as they move through matter. Some experiments have looked for monopoles trapped in magnetic materials, while others have searched for their tracks in cosmic ray detectors. If discovered, magnetic monopoles would revolutionize our understanding of fundamental physics and potentially enable new technologies based on magnetic phenomena. The ability to create isolated magnetic charges could lead to more efficient energy storage systems, novel approaches to particle acceleration, and deeper insights into the mathematical structure underlying physical reality. The ongoing search for these elusive particles continues to push the boundaries of experimental physics while highlighting the profound connections between symmetry, mathematics, and the fundamental nature of the universe we inhabit.
35 Lagrange points. Scattered throughout our solar system are special locations, called Lagrange points, where the gravitational influences of two massive objects create zones of perfect gravitational balance, allowing smaller objects to maintain stable positions relative to the larger bodies without requiring constant propulsion. These cosmic parking spots represent solutions to the three-body problem discovered by mathematician Joseph Louis Lagrange in 1772, revealing how gravitational forces can create regions of enhanced stability in otherwise chaotic orbital dynamics. Every system containing two massive objects orbiting their common center of mass possesses 5 Lagrange points, designated L1 through L5, each offering unique gravitational environments. The first 3 points lie along the line connecting the two massive bodies, while the fourth and fifth points form equilateral triangles with the two primary masses. These locations have become invaluable for space missions, providing energy-efficient staging areas for telescopes, satellites, and interplanetary spacecraft. The L1 point, located between the two massive objects, offers a unique vantage point for solar observation missions. The Solar and Heliospheric Observatory and the Deep Space Climate Observatory maintain positions at the Earth-Sun L1 point, approximately 1.5 million kilometers from Earth toward the Sun. From this location, spacecraft can continuously monitor solar activity and space weather while maintaining constant communication with Earth. L2 points provide ideal locations for space telescopes, requiring cold, stable environments shielded from solar radiation. The James Webb Space Telescope operates from the Earth-Sun L2 point. The L3 point lies on the opposite side of the primary mass from the smaller body, hidden from direct view. In the Earth-Sun system, L3 remains perpetually behind the Sun, as seen from Earth, making it an attractive location for science fiction scenarios involving hidden planets or monitoring stations. Though its practical utility for real missions remains limited due to communication challenges and orbital instabilities. L4 and L5 represent the most stable Lagrange points, forming equilateral triangles with the two primary masses. These locations can trap objects for millions or billions of years, creating natural collection points for asteroids, dust, and other debris. Jupiter SL4 and L5 points contain swarms of asteroids called Trojans that have remained in stable orbits for the entire history of the solar system. The gravitational balance at Lagrange points results from the complex interplay between gravitational attraction and centrifugal force experienced by objects orbiting the system's center of mass. At these special locations, the combined gravitational pull from both massive objects provides exactly the right centripetal force needed to maintain orbital motion, creating stable or semi-stable equilibrium points. Mission planners value Lagrange points for their energy efficiency, as spacecraft can maintain their positions with minimal fuel expenditure through small periodic corrections. This efficiency makes them ideal for long-duration missions requiring stable observation platforms or staging areas for deep space exploration. 36. Wormholes. Buried within Einstein's general theory of relativity lies one of the most captivating possibilities in theoretical physics. Wormholes, hypothetical tunnels through spacetime that could potentially connect distant regions of the universe, or even link separate universes entirely. These cosmic shortcuts, also known as Einstein-Rosen bridges, represent solutions to the equations of general relativity that describe curved spacetime geometries with exotic topological properties that challenge our intuitive understanding of space and time. The mathematical foundation for wormholes emerges from the same equations that predict black holes, but with a crucial difference in their internal structure. While black holes possess singularities at their centers, where spacetime curvature becomes infinite, wormholes would theoretically contain no singularities, instead featuring smooth geometric transitions that connect to distant regions through a tunnel-like passage. This fundamental distinction makes wormholes potentially traversable, at least in principle, unlike black holes which trap everything that crosses their event horizons. Constructing a stable, traversable wormhole would require exotic matter with negative energy density, a substance that violates the energy conditions that govern ordinary matter and energy. This exotic material would need to permeate the wormhole's throat, the narrowest section of the tunnel, preventing gravitational collapse and maintaining the passage against the natural tendency of spacetime to pinch off such connections. The energy requirements for creating and maintaining even microscopic wormholes would be enormous, potentially requiring the mass energy equivalent of entire stars. Quantum mechanics introduces additional complications for wormhole physics through vacuum fluctuations that could destabilize these space-time tunnels. Virtual particles constantly appearing and disappearing throughout empty space would tend to build up exponentially inside wormholes, creating a runaway feedback effect that could collapse the tunnel faster than light could traverse it. This quantum instability presents fundamental challenges to the practical realizability of macroscopic traversable wormholes. Despite these theoretical obstacles, wormholes continue to fascinate physicists because they represent natural solutions to Einstein's equations and could potentially enable faster-than-light travel without actually exceeding the speed of light locally. A wormhole would create a shortcut through higher-dimensional space, allowing travelers to reach distant destinations more quickly than light could travel through normal space, while never violating special relativity within their local reference frame. Some theoretical models suggest that microscopic wormholes might exist naturally at the quantum scale, constantly forming and dissolving in the quantum foam that comprises spacetime at the Planck length. These tiny passages would be far too small and short-lived to be traversable, but they might play important roles in quantum gravity, theories that attempt to unify general relativity with quantum mechanics. Advanced civilizations, if they exist, might theoretically be able to manipulate spacetime geometry to create artificial wormholes for interstellar transportation or communication. Such engineering projects would require mastery of exotic matter and energy sources beyond anything currently imaginable, representing the pinnacle of technological achievement for any species seeking to expand beyond their home solar system. The search for evidence of natural wormholes continues through gravitational wave astronomy and observations of exotic astronomical phenomena that might indicate the presence of these spacetime tunnels, connecting distant regions of our universe or linking us to other cosmic realms entirely. 37. Dark energy. Comprising approximately 68% of the universe's total energy content, dark energy represents the most profound mystery in modern cosmology. A completely unknown form of energy that appears to be accelerating the expansion of space itself. This cosmic component reveals its presence only through its gravitational effects on the largest scales, driving galaxies and galaxy clusters apart at ever-increasing rates, while remaining completely invisible to all forms of direct observation. The discovery of dark energy emerged from careful observations of distant supernova in the 1990s, when two independent research teams found that Type Ia supernova appeared dimmer than expected based on their redshifts. Since these stellar explosions serve as standard candles with well-understood lumen, their unexpected faintness indicated that they were farther away than cosmological models predicted. This observation revolutionized our understanding of cosmic evolution by revealing that the universe's expansion is accelerating rather than slowing down as previously assumed. The accelerating expansion, driven by dark energy, fundamentally challenges our understanding of gravity and energy. Unlike ordinary matter and radiation, which create attractive gravitational effects that should slow cosmic expansion, dark energy appears to exert a repulsive influence that overcomes the gravitational attraction of all visible and dark matter combined. This repulsive effect becomes more dominant as the universe expands and matter density decreases, suggesting that cosmic acceleration will continue indefinitely. The leading theoretical candidate for dark energy is vacuum energy, the quantum mechanical prediction that empty space contains zero-point fluctuations that contribute to the total energy density of the universe. However, naive calculations of vacuum energy density yield results that exceed observational constraints by more than 100 orders of magnitude, creating what physicists call the cosmological constant problem, and highlighting the enormous gaps in our understanding of quantum gravity and spacetime. Alternative explanations for dark energy include quintessence fields, hypothetical scalar fields that permeate space and change slowly over cosmic time. Unlike the cosmological constant, which remains perfectly constant, quintessence could evolve, potentially explaining why dark energy dominance emerged relatively recently in cosmic history. Some models suggest that quintessence might interact with dark matter, creating complex dynamics that could alter the future evolution of cosmic structure. The implications of dark energy for the ultimate fate of the universe are profound and somewhat unsettling. If dark energy continues to accelerate cosmic expansion at its current rate, the universe will experience exponential growth that eventually separates all gravitationally bound structures. Galaxies beyond our local group will disappear beyond the cosmic horizon, leaving future observers in a cold, empty universe with no evidence of the rich cosmic web that surrounds us today. More exotic possibilities include phantom dark energy scenarios, where the acceleration increases over time, potentially leading to a Big Rip event that would tear apart all structures in the universe, from galaxy clusters down to individual atoms. Alternatively, dark energy might decay or reverse its effects, leading to scenarios where cosmic expansion slows, stops, or even reverses into contraction. Current and planned observational programs aim to measure the properties of dark energy with unprecedented precision, potentially revealing whether it behaves like Einstein's cosmological constant or exhibits more complex dynamics that could provide clues to new physics beyond our current theoretical understanding. 38. Pulsars, spinning up to 700 times per second with clockwork precision that rivals atomic timepieces. Pulsars represent some of the most extreme objects in the universe. Neutron stars, whose powerful magnetic fields and rapid rotation create lighthouse beams of radiation that sweep across space. These cosmic metronomes formed from the collapsed cores of massive stars provide natural laboratories for testing fundamental physics under conditions of density, gravity, and magnetism that cannot be reproduced anywhere on Earth. Pulsars originate during supernova explosions, when stars more massive than about 8 times our Sun exhaust their nuclear fuel and undergo catastrophic gravitational collapse. In less than a second, the stellar core compresses from a sphere, roughly the size of Earth, to an object only 20 kilometers in diameter, creating matter so dense that a teaspoon would weigh as much as Mount Everest. This collapse concentrates the star's original magnetic field and angular momentum into an incredibly small volume, producing magnetic fields trillions of times stronger than Earth's and rotation periods measured in milliseconds. The characteristic pulsed emission from these objects results from the misalignment between their magnetic and rotational axes, similar to a lighthouse whose beam appears to flash as it rotates. Charged particles accelerated to nearly the speed of light along magnetic field lines emit intense beams of radio, optical X, and gamma-ray radiation that sweep across space with each rotation. When these beams pass across Earth, we observe regular pulses that arrive with extraordinary temporal precision. The discovery of pulsars in 1967 initially puzzled astronomers, because the regular radio pulses seemed almost artificial in their precision. Graduate student Jocelyn Bell Burnell and her advisor Anthony Hewish found signals that repeated every 1.3 seconds with such regularity that they briefly considered the possibility of extraterrestrial intelligence before recognizing the natural phenomenon they had uncovered. Pulsar timing observations have enabled remarkable tests of Einstein's general relativity and provided the first indirect evidence for gravitational waves. Binary pulsars, systems where a pulsar orbits another neutron star or stellar remnant, lose orbital energy precisely as predicted by general relativity through gravitational wave emission. The Holsteiler binary pulsar provided conclusive evidence for these ripples in spacetime decades before their direct detection by laser interferometers. Millisecond pulsars, spinning hundreds of times per second, likely achieved their extraordinary rotation rates through a recycling process involving mass transfer from binary companions. As material falls onto the neutron star's surface, it carries angular momentum that spins up the pulsar to incredible speeds, while simultaneously weakening its magnetic field through burial of magnetic flux beneath accreted material. The extreme physics of pulsar environments creates phenomena impossible elsewhere in the universe. Surface magnetic fields exceed those of laboratory magnets by factors of trillions, while gravitational fields approach strengths where general relativistic effects become dominant. Matter exists in exotic states, including superfluids and superconductors, that flow without resistance through the neutron star interior. Pulsar observations continue to advance our understanding of fundamental physics, serving as precision tools for detecting gravitational waves, testing theories of gravity, and exploring the properties of matter under extreme conditions that bridge astronomy and nuclear physics. 39. Sterile neutrinos. Beyond the 3 known types of neutrinos that permeate the universe in vast numbers, theoretical physics predicts the possible existence of sterile neutrinos, hypothetical particles that would interact even more weakly with ordinary matter than their already ghostly cousins. These elusive entities would participate only in gravitational interactions, making them nearly impossible to detect directly while potentially playing crucial roles in cosmic evolution, dark matter composition, and the fundamental structure of particle physics. Ordinary neutrinos, despite being among the most abundant particles in the universe, interact so weakly with matter that trillions pass through your body every second without leaving any trace. They participate only in weak nuclear interactions and gravity, making them extraordinarily difficult to study, despite their cosmic importance. Sterile neutrinos would be even more reclusive, interacting only through gravitational effects, and possibly through mixing with ordinary neutrinos under specific conditions. The theoretical motivation for sterile neutrinos emerges from several puzzling observations in neutrino physics that cannot be explained by the standard model of particle physics. Anomalous results from neutrino oscillation experiments suggest that neutrinos might transform into undetectable states during their journeys through space, implying the existence of additional neutrino species beyond the 3 known varieties. These sterile states would provide natural explanations for observed discrepancies in neutrino flux measurements. If sterile neutrinos exist with sufficient mass and stability, they could comprise some or all of the mysterious dark matter that dominates cosmic structure formation. Unlike ordinary dark matter candidates that require exotic new physics, sterile neutrinos would represent natural extensions of known particle families, providing elegant solutions to multiple cosmological puzzles simultaneously. Their weak interactions would allow them to cluster gravitationally, while remaining invisible to electromagnetic observations. The mass range for sterile neutrinos spans many orders of magnitude, depending on their proposed role in cosmic evolution. Light sterile neutrinos, with masses similar to ordinary neutrinos, could explain anomalies in neutrino oscillation experiments, while heavy sterile neutrinos weighing thousands of times more could serve as dark matter candidates. Intermediate mass sterile neutrinos might play important roles in supernova explosions and stellar evolution. Sterile neutrino dark matter would possess unique properties that distinguish it from other proposed dark matter candidates. These particles would be produced through quantum mechanical mixing with ordinary neutrinos in the early universe, creating a thermal relic abundance determined by fundamental particle physics rather than unknown interactions. This predictive power makes sterile neutrinos particularly attractive to theoretical physicists seeking natural dark matter explanations. Detection strategies for sterile neutrinos exploit their subtle interactions with ordinary neutrinos and their potential role as dark matter. X-ray telescopes search for characteristic emission lines that would appear if sterile neutrino dark matter decays in galaxy clusters and other massive structures. Neutrino oscillation experiments look for disappearance signals that could indicate transitions to sterile states. Laboratory searches for sterile neutrinos employ increasingly sensitive techniques to measure neutrino fluxes and oscillation patterns with unprecedented precision. These experiments probe parameter spaces where sterile neutrinos might reveal themselves through tiny deviations from standard model predictions, potentially opening new windows into physics beyond our current theoretical understanding. The discovery of sterile neutrinos would represent a monumental breakthrough in fundamental physics, potentially solving multiple cosmic mysteries, while revealing new aspects of the particle zoo that comprises reality at its most fundamental level. 40. Goldilocks zone. Surrounding every star in the universe lies a special region of space, where conditions might be just right for liquid water to exist on planetary surfaces, neither too hot to boil away, nor too cold to freeze solid. This habitable zone, playfully nicknamed the Goldilocks zone, after the fairy tale character who preferred things that were not too extreme, represents the cosmic sweet spot, where life as we understand it could potentially take root and flourish on rocky worlds orbiting their parent stars. The concept of habitable zones emerges from the fundamental requirements for life based on our understanding of biological processes on Earth. Water serves as the universal solvent for biochemistry, enabling the complex molecular interactions that drive living systems. For water to remain liquid on a planetary surface, temperatures must stay within a relatively narrow range between 0 and 100 degrees Celsius under Earth-like atmospheric pressures, constraining the orbital distances where potentially habitable worlds can exist. The boundaries of a star's habitable zone depend primarily on stellar luminosity, which determines how much energy reaches orbiting planets at various distances. More massive, luminous stars create larger habitable zones positioned farther from the stellar surface, while smaller, dimmer stars have habitable zones that hug closely to their surfaces. Our Sun's habitable zone extends roughly from the orbit of Venus to slightly beyond Mars, placing Earth comfortably within the zone where liquid water can persist. However, the habitable zone concept involves much more complexity than simple temperature calculations might suggest. Planetary atmospheres dramatically influence surface conditions through greenhouse effects, atmospheric composition, and circulation patterns that redistribute heat around the globe. Venus, technically within the solar habitable zone, experiences runaway greenhouse heating that maintains surface temperatures hot enough to melt lead, while Mars, near the outer edge, has lost most of its atmosphere and remains frozen despite occasional evidence of past liquid water. Tidal heating provides an alternative mechanism for maintaining habitable conditions beyond traditional habitable zones. Jupiter's moon Europa orbits well outside the Sun's habitable zone, yet gravitational flexing from its giant parent planet generates enough internal heat to maintain a subsurface ocean beneath its icy crust. This discovery has expanded our conception of habitable environments to include tidally heated moons around gas giant planets throughout the galaxy. The habitable zone concept continues evolving as astronomers discover the incredible diversity of exoplanetary systems. Super-Earths, rocky planets more massive than Earth, might maintain habitable surface conditions through enhanced greenhouse effects and volcanism. Planets with thick hydrogen atmospheres could remain warm enough for liquid water at distances far beyond traditional habitable zone boundaries through atmospheric heating mechanisms. Stellar evolution causes habitable zones to migrate over cosmic timescales. As stars age and brighten, their habitable zones move outward, potentially rendering formerly habitable worlds too hot, while bringing previously frozen planets into the zone where liquid water becomes possible. Our Sun will gradually expand its habitable zone outward over billions of years, eventually encompassing the orbits of Mars and the asteroid belt. The search for potentially habitable exoplanets focuses heavily on finding rocky worlds within their star's habitable zones, using transit photometry and radial velocity techniques to identify candidates for detailed atmospheric characterization. Future space telescopes will analyze the atmospheric compositions of these worlds, searching for water vapor, oxygen, and other biosignatures that might indicate the presence of life in these cosmic Goldilocks zones scattered throughout our galaxy. 41. Intermediate black holes. Between the stellar mass black holes that form from collapsing stars and the supermassive giants that anchor galactic centers lies a mysterious and elusive category known as intermediate black holes. Cosmic entities containing hundreds to hundreds of thousands of solar masses whose origins and properties challenge our understanding of black hole formation and evolution. These missing links in the black hole family tree have proven remarkably difficult to identify and study, creating one of astronomy's most persistent puzzles. The theoretical prediction of intermediate black holes emerges from the significant mass gap observed between stellar mass black holes, which typically contain 3 to 50 solar masses, and supermassive black holes weighing millions or billions of times more than our Sun. This enormous disparity in masses suggests that intermediate black holes should exist as evolutionary stepping stones, either as seeds that grow into supermassive giants, or as distinct populations formed through alternative mechanisms. Several formation pathways could theoretically produce intermediate black holes in the early universe and contemporary cosmic environments. Direct collapse scenarios propose that massive gas clouds in primordial galaxies could have collapsed directly into intermediate mass black holes without first forming stars, providing seeds for later supermassive black hole growth. Alternative models suggest that the first generation of extremely massive stars, potentially weighing hundreds of solar masses, could have formed intermediate black holes through direct collapse, or multiple stellar mergers in dense star clusters. The detection of intermediate black holes presents extraordinary observational challenges, because they produced weaker gravitational effects than supermassive black holes, while being much rarer than stellar mass objects. Traditional detection methods that work well for other black hole categories often fail in the intermediate mass range, requiring innovative observational strategies and extremely sensitive instruments to reveal their subtle signatures. Gravitational wave astronomy has opened new possibilities for discovering intermediate black holes through the detection of merger events. When two intermediate mass black holes spiral together and merge, they produce gravitational waves with characteristic frequencies and amplitudes that differ from both stellar mass and supermassive black hole mergers. Advanced gravitational wave detectors like LIGO and Virgo are beginning to probe the parameter space where such events might be detected. Some of the most promising intermediate black hole candidates have been found in globular clusters, ancient collections of stars that orbit in the halos of galaxies. These dense stellar environments provide ideal conditions for black hole formation through stellar collisions and mergers, potentially building up intermediate mass objects over billions of years. Observational evidence includes the high-velocity motion of stars in cluster cores and unusual X-ray emissions that could result from matter falling into hidden intermediate black holes. Ultraluminous X-ray sources represent another class of potential intermediate black hole candidates, emitting X-rays at luminosities that exceed what stellar mass black holes should be able to produce through standard accretion processes. While some of these objects might be explained by exotic stellar remnants or unusual accretion physics, others could harbor intermediate black holes consuming material from companion stars. The discovery and detailed study of intermediate black holes would fill crucial gaps in our understanding of black hole demographics and evolution, potentially revealing the pathways through which supermassive black holes formed in the early universe and continuing to grow throughout cosmic history. 42. Cyclic universe. Challenging the standard Big Bang cosmology that describes a universe with a definite beginning and ultimate end. Cyclic universe models propose that our cosmos undergoes endless cycles of expansion and contraction, creating an eternal sequence of cosmic rebirths that stretches infinitely into both the past and future. These elegant theoretical frameworks attempt to resolve fundamental questions about cosmic origins, while avoiding the conceptual difficulties associated with absolute beginnings and endings. The modern concept of cyclic cosmology builds upon ancient philosophical traditions that viewed time as circular rather than linear, but incorporates sophisticated physics, including general relativity, quantum mechanics, and string theory, to create mathematically rigorous models of cosmic evolution. These theories suggest that what we perceive as the Big Bang actually represents a cosmic bounce, a transition point where a previous contracting universe reached maximum density and began expanding once again. Cyclic models typically involve extra-spatial dimensions beyond the familiar 3 dimensions of everyday experience, with our 4-dimensional universe existing as a membrane or brane embedded within higher dimensional space. In ekpyrotic scenarios, cosmic cycles result from periodic collisions between parallel branes separated by tiny distances in the extra dimensions. These collisions provide the energy and initial conditions needed to restart cosmic expansion, creating new cycles without requiring infinite energy or matter creation. The cyclic approach elegantly addresses several puzzles that challenge standard Big Bang cosmology. The flatness problem, which questions why the universe appears to have exactly the critical density needed for flat geometry, finds natural resolution in cyclic models, where repeated expansion and contraction cycles gradually drive the universe toward optimal conditions. Similarly, the horizon problem, concerning the remarkable uniformity of the cosmic microwave background across regions that should never have been in causal contact, becomes less problematic if these regions were in thermal equilibrium. During previous cosmic cycles, dark energy, the mysterious component driving accelerated cosmic expansion, plays a crucial role in many cyclic scenarios. Rather than remaining constant forever, dark energy in these models eventually decays or reverses its effects, causing cosmic expansion to slow, stop, and reverse into contraction. This cosmic turnaround initiates a new phase of evolution, leading toward the next bounce event, maintaining the eternal cycle of cosmic death and rebirth. Quantum mechanics introduces additional complexity to cyclic models through the behavior of matter and energy during the bounce phase. As the universe contracts toward maximum density, quantum effects become increasingly important, potentially preventing the formation of classical singularities and enabling smooth transitions between contraction and expansion phases. These quantum bounces might preserve information and structure from previous cycles, creating subtle imprints that could theoretically be observed in the cosmic microwave background or other relics of cosmic history. Observational tests for cyclic cosmology focus on detecting signatures that would distinguish these models from standard inflationary Big Bang scenarios. Gravitational wave signatures from the bounce phase, specific patterns in primordial density fluctuations, or unusual properties of dark energy evolution could provide evidence for cyclic behavior, though such observations remain at the limits of current technological capabilities. The philosophical implications of cyclic universes are profound, suggesting that cosmic history extends infinitely in both directions, without ultimate beginnings or endings, creating an eternal cosmic dance of expansion and contraction that encompasses all possible physical processes and evolutionary pathways. 43. Supernova remnants. Scattered throughout our galaxy like cosmic monuments to stellar death, supernova remnants represent the expanding shockwaves and debris clouds left behind when massive stars end their lives in catastrophic explosions. These spectacular structures, glowing with the light of superheated gas and accelerated particles, serve as cosmic recycling centers that enrich the interstellar medium with heavy elements, while creating some of the most energetic phenomena observable in the electromagnetic spectrum. The formation of supernova remnants begins with the violent core collapse of stars, more massive than about 8 solar masses. Events that release more energy in seconds than our sun will produce over its entire 10 billion year lifetime. The explosion propels stellar material outward at speeds exceeding 10,000 kilometers per second, creating shockwaves that sweep up surrounding interstellar gas and dust while heating it to temperatures of millions of degrees. During their early evolution, supernova remnants expand as roughly spherical shells of hot, ionized gas that glow brilliantly in X-ray wavelengths due to their extreme temperatures. The Sadov-Taylor phase, lasting several thousand years, describes this period when the expanding shockwave encounters and accelerates interstellar material, creating characteristic bubble-like structures that can grow to diameters exceeding 100 light-years before beginning to cool and fade. The interaction between supernova shockwaves and the surrounding interstellar Medium creates complex structures visible across the electromagnetic spectrum. Optical emission arises when shock-heated gas cools and recombines, producing characteristic spectral lines from hydrogen, oxygen, and other elements. Radio emission results from high-energy electrons spiraling through magnetic fields, while X-ray observations reveal the hottest gas in the remnant interior and the locations of continued shock heating. Supernova remnants serve as the primary cosmic factories for accelerating particles to extremely high energies, potentially explaining the origin of galactic cosmic rays that permeate interstellar space. The turbulent magnetic fields and shock fronts within these structures can accelerate protons and heavier nuclei to speeds approaching the speed of light through a process called diffusive shock acceleration. These energetic particles eventually escape into the broader galaxy, contributing to the cosmic ray background that influences stellar formation and galactic dynamics. The chemical enrichment provided by supernova remnants represents one of their most important cosmic functions. The nuclear fusion processes that powered massive stars throughout their lives create elements heavier than hydrogen and helium, including the carbon, oxygen, silicon, and iron that comprise rocky planets and biological systems. When these enriched stellar cores explode, they distribute their nucleosynthetic products throughout the surrounding interstellar medium, making them available for incorporation into future generations of stars and planetary systems. Different types of supernova produce distinct remnant characteristics and element abundances. Core collapse supernova from massive stars create neutron-rich environments that favor the production of elements like titanium and nickel through explosive nucleosynthesis. Type EAA supernova, resulting from exploding white dwarf stars, generate large quantities of iron peak elements through thermonuclear burning, creating remnants with different spectral signatures and chemical compositions. The Crab Nebula represents perhaps the most famous supernova remnant, created by a stellar explosion observed by Chinese astronomers in the year 1054. At its center lies a pulsar, the rapidly spinning neutron star remnant of the original explosion, whose energetic radiation continues to power the nebula's glow nearly 1,000 years after the initial event. As supernova remnants age and expand, they gradually merge with the surrounding interstellar medium, dispersing their enriched material and energy throughout the galaxy, while leaving behind the compact stellar remnants that mark the end of their progenitor stars' lives. 44. Cosmic strings. Among the most exotic theoretical objects predicted by modern physics, cosmic strings represent hypothetical one-dimensional defects in the fabric of space-time itself, incredibly thin filaments of concentrated energy that could stretch across vast cosmic distances while possessing mass densities comparable to atomic nuclei. These cosmic threads, if they exist, would create some of the most extreme gravitational environments in the universe, while potentially providing observational windows into the physics of the earliest moments after the Big Bang. The theoretical foundation for cosmic strings emerges from grand unified theories and string theory, which suggests that phase transitions in the early universe could have created topological defects in space-time geometry. Just as imperfections form when water freezes into ice, the cooling universe might have developed cosmic strings as boundaries between regions that settled into different vacuum states during symmetry-breaking transitions in the fundamental forces. Cosmic strings would possess truly extraordinary properties that challenge human intuition about the nature of matter and space. Despite being thinner than atomic nuclei, these objects could contain enormous amounts of energy concentrated into their one-dimensional structure, creating linear mass densities equivalent to millions of tons per meter of length. A cosmic string spanning the observable universe would contain more mass than typical galaxies, while remaining essentially invisible to electromagnetic observations. The gravitational effects of cosmic strings would differ dramatically from those of ordinary matter, creating unusual space-time geometries that could produce observable signatures through their influence on light and matter. Unlike spherical mass distributions that create curved space-time in all directions, cosmic strings would generate gravitational effects primarily in the plane perpendicular to their length, creating deficit angles in space-time that could focus light in characteristic patterns. Moving cosmic strings would generate gravitational waves through their oscillations and interactions, creating ripples in space-time that could theoretically be detected by sensitive gravitational wave observatories. The collision or intersection of cosmic strings would produce particularly violent gravitational wave bursts, releasing enormous amounts of energy in brief events that might appear as transient signals in detector networks, like LIGO and Virgo. If cosmic strings formed networks in the early universe, their evolution would be governed by complex dynamics, involving stretching due to cosmic expansion, reconnection events when strings intersect, and the formation of loops that could later decay through gravitational wave emission. Computer simulations suggest that such networks would reach scaling solutions, where their average properties remain constant despite ongoing cosmic expansion. Observational searches for cosmic strings focus on several potential signatures that these objects might produce in astronomical observations. Gravitational lensing effects could create characteristic patterns when light passes near cosmic strings, producing double images of distant galaxies aligned along straight lines. The Kaiser-Stebbins effect predicts that cosmic strings should create specific temperature patterns in the cosmic microwave background radiation through their gravitational influence on photons. High-energy cosmic string phenomena might also produce observable consequences. When cosmic string loops decay, they could generate bursts of high-energy particles and electromagnetic radiation, potentially contributing to unexplained cosmic ray events, or gamma-ray bursts. Some theoretical models suggest that cosmic strings might even serve as seeds for primordial black hole formation, or create exotic matter states with unusual properties. The discovery of cosmic strings would provide unprecedented insights into fundamental physics at energy scales far beyond what terrestrial particle accelerators can achieve, potentially revealing the mathematical structure underlying spacetime and confirming theoretical predictions about the earliest moments of cosmic history. 45. Cosmic dust. Pervading the space between stars throughout our galaxy and beyond. Cosmic dust consists of tiny solid particles ranging in size from large molecules to microscopic grains, created by stellar winds, supernova explosions, and planetary collisions. These minute fragments of matter play crucial roles in cosmic evolution, serving as the raw material for planet formation, while significantly influencing stellar birth, galactic dynamics, and our observations of the distant universe. The composition of cosmic dust reflects the diverse stellar processes that created it over billions of years of galactic evolution. Silicate grains formed in the atmospheres of dying red giant stars carry signatures of stellar nucleosynthesis, while carbonaceous particles created by carbon-rich stars contribute organic compounds that serve as building blocks for complex chemistry. Metallic grains produced in supernova explosions add iron, nickel, and other heavy elements to the interstellar mixture, creating a heterogeneous population of particles with varied properties. Individual dust grains typically measure between nanometers and micrometers in diameter, making them comparable in size to the wavelength of visible light. This size relationship enables cosmic dust to interact strongly with starlight through scattering and absorption processes that redden and dim distant stars, creating the interstellar extinction that challenges astronomical observations. The characteristic reddening occurs because dust particles scatter blue light more efficiently than red light. Similar to how Earth's atmosphere creates colorful sunsets within dense molecular clouds where stars form, cosmic dust serves essential functions that enable the gravitational collapse necessary for stellar birth. Dust grains provide cooling mechanisms that allow gas clouds to contract by radiating away thermal energy in infrared wavelengths. They also serve as catalysts for chemical reactions that would be impossible in pure gas, enabling the formation of molecular hydrogen and other compounds essential for star formation processes. The role of cosmic dust in planet formation represents one of its most important cosmic functions. Within protoplanetary disks surrounding young stars, dust particles stick together through electrostatic forces and gentle collisions, gradually building up larger aggregates. These dust bunnies continue growing through accretion and gravitational attraction, eventually forming planetesimals, and ultimately terrestrial planets like Earth. Different regions of protoplanetary disks produce distinct types of dust processing and grain growth. Close to the central star, high temperatures vaporize volatile compounds and alter grain compositions through thermal processing. The snow line, where water ice condenses, marks a crucial boundary that influences the types of planets that can form at various orbital distances, with rocky planets forming interior to this line, and gas giants typically forming beyond it. Cosmic dust also serves as a tracer of galactic structure and evolution, revealing the distribution of star-forming regions and the pathways of material flow throughout galaxies. Infrared observations of dust emission map the spiral arms of galaxies and identify regions of active stellar birth, while measurements of dust-to-gas ratios provide insights into the chemical evolution and metallicity gradients that characterize galactic environments. Interplanetary dust within our solar system originates from asteroid collisions, comet tails, and debris from planetary formation processes. This material creates the zodiacal light visible before dawn and after sunset. When sunlight scattered by dust particles creates a faint glow along the ecliptic plane, spacecraft and meteors constantly encounter this dust, providing samples that reveal the composition and history of our solar system's formation. The study of cosmic dust connects multiple scales of cosmic evolution, from the nucleosynthetic processes in stellar interiors that create dust-forming elements to the large-scale structure of galaxies shaped by dust-mediated star formation, creating a comprehensive picture of how matter cycles through cosmic environments over billions of years. 46. Black hole information paradox. At the intersection of general relativity and quantum mechanics lies one of theoretical physics' most profound puzzles, the black hole information paradox, a fundamental contradiction that challenges our understanding of how information behaves in the universe and threatens the mathematical consistency of physics itself. This paradox emerges from the apparent conflict between quantum mechanics, which demands that information cannot be destroyed, and Stephen Hawking's discovery that black holes eventually evaporate completely through quantum radiation. The information paradox begins with the principle of unitarity in quantum mechanics, which states that the total information content of any physical system must be preserved throughout all quantum processes. In practical terms, this means that if you know the complete quantum state of a system at one time, the laws of physics should allow you to calculate its state at any other time, either forward or backward. This conservation of quantum information represents one of the fundamental pillars of quantum theory. When matter falls into a black hole, it appears to disappear behind the event horizon, taking its quantum information beyond the reach of outside observers. According to classical general relativity, this information becomes permanently inaccessible, trapped within the black hole until the end of time. However, Hawking's revolutionary insight revealed that quantum effects near the event horizon cause black holes to emit thermal radiation and gradually evaporate, eventually disappearing completely. The thermal nature of Hawking radiation creates the heart of the information paradox. Thermal radiation carries no information about the specific matter that created it. Much like the random heat given off by a burning book carries no information about the words that were written on its pages. If black holes emit purely thermal radiation until they completely evaporate, the quantum information that fell into them would appear to be destroyed forever, violating the fundamental principle of unity. Several proposed resolutions to the information paradox have emerged from decades of theoretical research, each with profound implications for our understanding of spacetime and quantum mechanics. The complementarity principle suggests that information never actually crosses the event horizon from the perspective of outside observers, instead remaining encoded on the black hole's surface, in a scrambled form that eventually emerges in the Hawking radiation through subtle correlations. Holographic theories propose that the information falling into black holes becomes encoded on their two-dimensional surfaces rather than in their three-dimensional interiors, similar to how holograms store three-dimensional images in two-dimensional media. This holographic principle suggests that the apparent three-dimensional interior of black holes might be an emergent phenomenon rather than fundamental reality, resolving the paradox by eliminating the distinction between interior and exterior information storage. More radical solutions include the possibility that black holes do not have interiors at all, existing instead as highly excited quantum states of matter concentrated near what would classically be the event horizon. These fuzzball models suggest that quantum effects prevent the formation of classical event horizons and singularities, maintaining all information in accessible forms throughout the black hole's evolution. The firewall paradox represents a recent development that further complicates attempts to resolve the information puzzle. This argument suggests that maintaining quantum information conservation requires the event horizon to be replaced by a wall of high-energy radiation that would incinerate anything attempting to cross it, contradicting Einstein's equivalence principle and challenging our understanding of what falling into black holes would actually entail. Resolution of the information paradox will likely require revolutionary advances in our understanding of quantum gravity, the theoretical framework needed to unify general relativity with quantum mechanics and describe the physics of extreme spacetime curvature, where classical concepts break down. 47. The observable universe. Extending approximately 46.5 billion light-years in every direction from Earth, The observable universe represents the finite cosmic region from which light has had sufficient time to reach us since the Big Bang, creating a spherical boundary that defines the limits of what we can see and study through astronomical observations. This cosmic horizon results not from the edge of space itself, but from the finite age of the universe and the speed of light, creating a fundamental limit on how far we can peer into the cosmic depths. The concept of the observable universe emerges from the interplay between cosmic expansion and the travel time of electromagnetic radiation across vast distances. While the universe may be infinite in extent, we can only observe objects whose light has had enough time to traverse the expanding space between them and Earth. During the 13.8 billion years since the Big Bang, this creates a spherical region centered on our location that serves as our cosmic window into the broader universe. The radius of the observable universe exceeds the simple calculation of the speed of light multiplied by the age of the universe, because cosmic expansion has stretched the space between distant objects and Earth, while their light traveled toward us. Objects that emitted light shortly after the Big Bang have continued moving away from us due to the expansion of space itself, meaning they are now much farther away than their light travel time would suggest. This expansion effect increases the current distance to the edge of the observable universe to nearly 3 times what a naive calculation would predict. The cosmic microwave background radiation represents the most distant observable phenomenon, originating from the surface of last scattering, when the universe first became transparent to light approximately 380,000 years after the Big Bang. This ancient glow surrounds us from all directions, carrying information about the conditions that existed when atoms first formed and providing our deepest view into cosmic history. Beyond this cosmic photosphere, the universe remains opaque to electromagnetic observations. Within the observable universe, astronomers estimate that there are approximately 2 trillion galaxies, each containing hundreds of billions of stars and potentially countless planetary systems. These galaxies organize themselves into a cosmic web of filaments and voids that spans the largest scales of cosmic structure, creating patterns that reflect the quantum fluctuations present during cosmic inflation in the first fraction of a second after the Big Bang. The observable universe contains profound mysteries that highlight the limitations of our cosmic perspective. Dark matter and dark energy, which together comprise approximately 95% of the universe's total mass energy content, remain invisible to electromagnetic observations and reveal themselves only through their gravitational effects on visible matter and cosmic expansion. These dark components suggest that most of the universe consists of physics that we do not yet understand. Cosmic horizons create several types of boundaries that limit different aspects of our observational reach. The particle horizon defines the maximum distance from which light could have reached us, while the event horizon represents the boundary beyond which events will never become observable due to accelerating cosmic expansion driven by dark energy. Objects beyond the event horizon are receding faster than light can approach us through expanding space. The concept of cosmic inflation suggests that the actual universe extends far beyond our observable horizon, possibly by many orders of magnitude or even infinitely. The observable universe might represent an infinitesimally small fraction of a much larger cosmic structure that remains forever beyond our observational reach, containing regions with potentially different physical properties or evolutionary histories. Future observations will gradually expand our observable universe as light from increasingly distant objects reaches Earth. But cosmic expansion ensures that we will never see beyond the surface of last scattering that created the cosmic microwave background, maintaining this fundamental limit on our electromagnetic window into cosmic history. 48. Quasars, among the most luminous and distant objects in the universe. Quasars represent supermassive black holes in the centers of ancient galaxies that are actively consuming enormous amounts of material and converting it into energy with extraordinary efficiency. These cosmic beacons can outshine their entire host galaxies by factors of hundreds, while remaining point-like in appearance due to their tremendous distances, creating some of the most extreme astrophysical environments observable anywhere in the cosmos. The name quasar originates from quasi-stellar radio source, reflecting the initial discovery of these objects as powerful radio emitters that appeared star-like in optical telescopes, despite their enormous distances and luminosities. When astronomers first measured the redshifts of quasars in the 1960s, they found that these objects were receding at significant fractions of the speed of light, indicating distances of billions of light-years and luminosities that challenged conventional understanding of astrophysical energy sources. The extraordinary power output of quasars results from the gravitational accretion of material onto supermassive black holes containing millions to billions of solar masses. As gas, dust, and even entire stars spiral inward through an accretion disk, gravitational energy converts to thermal energy with remarkable efficiency, heating the enfolding material to temperatures exceeding millions of degrees. This superheated matter glows brilliantly across the entire electromagnetic spectrum, from radio waves to gamma rays, creating the multi-wavelength signatures that characterize active galactic nuclei. The accretion disks surrounding quasar black holes represent some of the most efficient energy conversion mechanisms in the universe, transforming roughly 10% of infalling matter directly into radiant energy through the release of gravitational potential energy. This efficiency exceeds nuclear fusion by more than an order of magnitude, explaining how relatively compact regions can generate luminosities equivalent to hundreds of billions of stars, while consuming only modest amounts of material. Many quasars exhibit powerful relativistic jets of plasma that extend for hundreds of thousands of light-years from their central black holes, carrying tremendous amounts of energy and momentum into the surrounding intergalactic medium. These jets form when magnetic fields threading the accretion disk and black hole ergosphere accelerate charged particles to speeds approaching the speed of light, creating collimated beams that can remain coherent across enormous distances. The orientation of quasar jets relative to Earth significantly influences their observed properties, creating different classes of active galactic nuclei based on viewing angle effects. When jets point directly toward us, relativistic beaming enhances their apparent luminosity and creates blazards with rapidly variable emission. Side-on views reveal the full extent of radio lobes inflated by jet interactions with intergalactic gas, while edge-on orientations can obscure the central engine behind dusty torus structures. Quasars serve as invaluable cosmological probes due to their extreme luminosities and great distances, providing information about conditions in the early universe when galaxies were first forming and evolving. The most distant quasars observed date back to when the universe was less than 1 billion years old, revealing that supermassive black holes achieved enormous masses remarkably quickly after the Big Bang through processes that remained poorly understood. The relationship between quasars and galaxy evolution represents an active area of astronomical research, with mounting evidence that supermassive black holes and their host galaxies co-evolve through feedback mechanisms involving both accretion and jet activity. Quasar outflows can regulate star formation by heating and dispersing gas throughout galactic environments, while also enriching the intergalactic medium with heavy elements produced in stellar nucleosynthesis. Modern surveys have catalogued hundreds of thousands of quasars across cosmic history, revealing how their population evolved as the universe aged and gas supplies for feeding central black holes gradually became exhausted, causing the quasar era to fade as galaxies matured into their current, relatively quiescent states. 49. Antimatter. For every particle of ordinary matter in the universe, theoretical physics predicts the existence of a corresponding antiparticle with opposite electric charge and other quantum properties, creating antimatter that annihilates with normal matter in spectacular displays of pure energy conversion. This mirror world of particles represents one of the most profound symmetries in nature, while posing one of cosmology's deepest mysteries. Why does our universe appear to be dominated by matter, rather than containing equal amounts of matter and antimatter, as fundamental physics seems to require? The discovery of antimatter emerged from Paul Dirac's attempts to reconcile quantum mechanics with special relativity in the late 1920s. His relativistic quantum equation predicted that electrons should have positive energy states that we observe in nature, but also negative energy states that initially seemed meaningless. Dirac eventually realized that these negative energy solutions represented positrons, particles identical to electrons except for their positive electric charge. When matter and antimatter particles meet, they undergo mutual annihilation that converts their entire rest mass into energy, according to Einstein's famous equation, E equals mc squared. This process represents the most efficient energy conversion mechanism possible in physics, completely transforming matter into radiation with perfect efficiency. The annihilation of a single electron and positron produces two high-energy gamma rays that carry away the energy equivalent of both particles' masses. Antimatter exists naturally in our universe through several production mechanisms, though in quantities far smaller than ordinary matter. Cosmic ray interactions with atmospheric nuclei regularly create positrons and antiprotons that rain down on Earth's surface in tiny amounts. Certain types of radioactive decay also produce positrons, while high-energy, Astrophysical environments, like pulsar magnetospheres and active galactic nuclei, can generate significant quantities of antimatter particles. The extreme rarity of antimatter in the observable universe creates the baryon asymmetry problem, one of the most significant unsolved puzzles in cosmology. If the Big Bang produced equal amounts of matter and antimatter as symmetry principles suggest, these particles should have completely annihilated each other, leaving behind a universe containing only radiation. The fact that we exist in a matter-dominated cosmos indicates that some unknown process created a slight excess of matter over antimatter during the early universe. Proposed solutions to the baryon asymmetry problem require violations of fundamental symmetries that govern particle interactions. The Sakharov conditions specify that baryon number violation, charge parity violation, and departure from thermal equilibrium must all occur simultaneously to generate the observed matter-antimatter imbalance. While the standard model of particle physics contains some of these ingredients, the effects appear too small to explain the magnitude of asymmetry we observe. Laboratory production and study of antimatter requires sophisticated particle accelerators and magnetic confinement systems due to the immediate annihilation that occurs when antimatter contacts ordinary matter. The European Organization for Nuclear Research regularly produces antiprotons and positrons for fundamental physics research, including precision tests of the symmetries between matter and antimatter, and investigations of antimatter's gravitational behavior. Antimatter applications in medicine and technology exploit the precise energy release from annihilation reactions. Positron emission tomography uses positrons emitted by radioactive traces to create detailed images of metabolic activity within living tissue. Theoretical antimatter propulsion systems could achieve extraordinary specific impulses for spacecraft, though the engineering challenges of antimatter production, storage, and handling remain formidable. The search for antimatter galaxies, or cosmic regions dominated by antimatter, continues. Through observations of Gamera signatures that would result from matter-antimatter boundaries in space, though no convincing evidence for large-scale antimatter structures has been found, supporting the conclusion that our observable universe consists almost entirely of ordinary matter despite the fundamental symmetries that suggest otherwise. 50. Panspermia. The hypothesis that life might spread throughout the universe through the transfer of microorganisms, spores, or genetic material between planetary bodies, offers a provocative alternative to the conventional view that life arises independently on each world where suitable conditions exist. This concept of panspermia suggests that biology might be a cosmic phenomenon that propagates across interstellar and even intergalactic distances, potentially connecting the evolutionary histories of widely separated worlds through shared biological heritage. The modern scientific formulation of panspermia builds upon the remarkable resilience that certain microorganisms demonstrate under extreme conditions that would be lethal to complex life forms. Extremophile bacteria and archaea can survive intense radiation, extreme temperatures, desiccation, and chemical environments that approach the harsh conditions of interplanetary and interstellar space. Some organisms enter cryptobiotic states where metabolic activity essentially stops, allowing them to remain viable for extended periods until favorable conditions return. Laboratory experiments have demonstrated that various microorganisms can survive simulated space conditions, including the vacuum of space, intense ultraviolet radiation, and cosmic ray bombardment. Tardigrades, microscopic animals, known as water bears, have survived direct exposure to the space environment during orbital experiments, while bacterial spores have shown remarkable longevity under conditions that approximate interplanetary travel scenarios. Natural mechanisms exist that could potentially transport biological material between planetary bodies within solar systems and possibly between nearby star systems. Impact events that excavate material from planetary surfaces can accelerate rocks to escape velocity, sending them on trajectories that could reach other worlds. Mars meteorites found on Earth demonstrate that such interplanetary transport occurs, raising the possibility that microorganisms embedded within these rocks could survive the journey between worlds. The timeline for interplanetary transport within our solar system ranges from months to millions of years, depending on the specific trajectories and gravitational interactions involved. While brief journeys might allow active microorganisms to survive, longer transit times would require organisms in dormant states to maintain viability throughout extended exposure to space radiation and temperature extremes. Interstellar panspermia presents far greater challenges due to the vast distances and extended travel times involved in journeys between star systems. Even the fastest natural ejection velocities would require millions of years to reach the nearest stars, testing the limits of biological survival under space conditions. However, some bacterial spores have demonstrated viability over geological timescales when properly protected, suggesting that interstellar biological transport might be theoretically possible. Directed panspermia represents a variant hypothesis, proposing that intelligent civilizations might deliberately seed other worlds with life, either as exploratory ventures or as attempts to preserve biological heritage. This scenario could explain the rapid emergence of complex life on Earth, and might account for certain biochemical universals that characterize terrestrial biology. The search for evidence of panspermia focuses on detecting biological signatures that might indicate common evolutionary origins for life on different worlds. Shared biochemical features, genetic sequences, or metabolic pathways between Earth life and potential extraterrestrial organisms could provide compelling evidence for biological relationships that transcend individual planetary environments. If validated, panspermia would profoundly alter our understanding of astrobiology and the distribution of life throughout the universe. Rather than being isolated evolutionary experiments, living worlds might participate in a vast biological network that spans cosmic distances and timescales, creating opportunities for biological diversity and complexity that exceed what individual planets could achieve through independent evolution. The implications of panspermia extend beyond biology to encompass planetary protection protocols for space missions, the interpretation of potential biosignatures detected on exoplanets, and the development of strategies for searching for life throughout the cosmos.